Good day, ladies and gentlemen, and welcome to day one of the Next Generation Resources 2020 Student Conference. My name is Michael Odidi, and I am streaming to you from the beautiful city of Cape Town. I have the honor of being the very first voice that you hear, but I am not alone. Behind the scenes, there have been a group of students who have worked tirelessly to bring you this showcase. What makes this special is that this is a collaboration of four different universities from around the world: the University of British Columbia in Canada, the University of Exeter in the UK, the University of Cape Town in South Africa, and of course, the University of Queensland in Australia, who have played physical host to this event in many in previous years. However, due to the current situation, the COVID-19 pandemic, we, like so many others, have had to rethink the structure of the conference this year. So we have decided to go completely virtual. And based on the overwhelmingly positive responses that we got, we definitely think we made the right choice. Prior to this showcase, we have received close to 40 video presentations and have decided to compile them in a YouTube playlist called Next Generation Resources 2020. The links to the different presentations can be found in our digital compilation or ebook of abstracts found on our LinkedIn page or soon on the SMI website. I would like to encourage everyone to please take the time out to check out all of the presentations we received, because unfortunately, due to time limitations, we can only show 18 of those presentations across our two live showcase events. 9 of those will be shown today, and the other 9 will be shown in approximately 12 hours from the end of this showcase. This was done to accommodate for the different time zones that our participants from all over the world find themselves in. A stringent selection criterion was used to ensure that the process was fair and as transparent as possible. Now, the theme of this conference is aptly summarized with the statement, breaking today's silos for tomorrow's resources. Let me repeat, breaking today's silos for tomorrow's resources. Interesting, huh? I could elaborate, but where's the fun in that? If I have piqued your curiosity, which I hope I have, then stay tuned, because not only do we have exciting video presentations from students all around the world, we will also be having thought-provoking and informative panel discussions in which experts from the different fields in the minerals industry will be sharing their ideas on what they think the future of mining holds. I am sure that what they have to say is going to inspire much debate and stimulate lots of conversations. So I think this is a good time to remind and encourage all of our attendees to please utilize the Q&A function. What I mean is, if you find yourself during the conference having an aha moment, as Oprah would say, or you have a burning question, or you simply just want to express your opinion on the various subject matters, please do make use of those tools, and we will try our very best to ensure that all questions are addressed, either live or via the chat. Remember, this is your conference, so please stay engaged. Also, I would like to just let the audience know, we will be running a poll in which the audience will get to choose the best presentation. So in the interest of fairness, please take the time out to listen to all of the video presentations that we show in this live showcase. And at the end of the showcase, you will get the option to choose or select your best or favorite presentation. So please, before making your choice, listen to everything. And I promise you, it is all definitely worth your time. Now, ladies and gentlemen, without further ado, I would like to introduce our very first keynote speaker, Professor Neville Plint from the University of Queensland, Australia. Professor Plint is the director of the Sustainable Minerals Institute at the university. He holds a PhD and an MBA with distinction from the University of Witwatersrand in Johannesburg, South Africa. So we South Africans can partly claim him as ours. He brings extensive leadership and experience with a deep understanding of the mining sector, having worked for 20 years with Anglo American in South Africa. Professor Plint's extensive background focused on delivering improved operational performance on mining sites by developing and implementing new technologies, whilst establishing a global network of research professionals in academic institutes, mining companies, and research organizations. We are really excited to hear what he has to say. So everyone, please join me in welcoming Professor Neville Plint. Professor, the virtual floor is yours.
Michael, thank you very much, and thank you very much for the kind introduction. And absolutely, very, very proud South African, and very proud of the team at Cape Town that have done fantastic work at working with us to pull this program together. I would like to start by acknowledging the traditional owners and their custodianship of the land on which we meet virtually today. On behalf of the Sustainable Minerals Institute, I pay our respects to their ancestors and their descendants who continue cultural and spiritual connections to country. We recognise their valuable contributions to Australia and the global society. I was just reflecting a minute or two ago as to how did we end up with this conference. And the origin of this was a conversation with a visiting academic from Canada, Tony Hodge, who really spent some time with our postgrad students and said that one of the skills that we all need to master is the one of social media and media in general, and getting our message across. And I've been working with Sue Harrison, Scott Dunbar, and Ken Evans at Exeter, thinking about how we could bring our organizations together to work virtually on the global challenges facing the industry. And we decided that a student conference where we could have physical presentations as well as virtual presentations or digital presentations was a really, really good thing to do. And we had a go at it last year, and the teams, the international teams, did a fantastic job, and we were very fortunate to have a number of visitors make it to Brisbane. So the idea was to do that again this year. And of course, the COVID pandemic stepped in, but it also gave us an incredible opportunity for all of us to experience and to try and master this new digital or virtual world, and really work on our communication skills and how we can get across the messages of the fantastic research that's been done across all the organizations. So to everybody that submitted presentations, I really, really would like to thank you. I know what's involved in putting something like this together. It's purely voluntary. I know you had to take time out of your studies to do it, but it's an incredible showcase, and I think you could all be unbelievably proud of what you've delivered, and really looking forward to the presentations this evening and tomorrow. I would like to acknowledge the sponsors. We've been very fortunate over the years that the industry has supported our endeavours and are very keen on supporting our postgraduate students. And I'd like to thank Ausenco and Ware Minerals, who sponsored the event, as well as the JK Tech, who is our commercialization and technology transfer partner within the Sustainable Minerals Institute. So thank you very much to them. And as I said, I'd like to thank Sue, Scott, and Ken for their support. Without their support at the executive level, it's very difficult to make something like this really happen. And then to Daniel Franks, who very kindly stepped in and took the lead from the SMI point of view, just to work with the postgraduates to bring it together. And to the Next Gen Organising Committee, I think you guys are fantastic. I think you've done an incredible job. I don't want to prejudge the next 2 days, but it's been a real absolute pleasure just watching you putting this conference together and connecting. And well done, and a virtual congratulations. And I think you could be very proud of what you've done. And then to all the panelists that have given up their time to participate and to add alternative perspectives from your experience, hugely valuable. We're all really interested in hearing what you have to say and what guidance you have for us. So look forward to those panels. I think I'm going to stop now and hand back to you, Michael, so that we can get going and we can stay on track. I know we've got a very tight agenda. So thank you to everybody. Looking forward to the presentations. And I suppose it is good luck, although it's all recorded. Thanks, Michael.
Thank you very much, Professor. That definitely has set the mood for what is to come. Our very first session that we're going to be dealing with today has to deal with novel approaches to mining. Novel approaches to mining. And our first presentation is from Joshua Racera, who is from the Imperial College in London. And the title of his presentation is called Space Resources Towards a Sustainable Future in Space and on Earth. space resources towards a sustainable future in space and on Earth. Ladies and gentlemen, please welcome, or please enjoy, Joshua Racera's video.
Hello, my name is Joshua Racera, and I am a third-year PhD student in the Space and Terrestrial Resources Group at Imperial College London. Today, I will be speaking to you about how the development of technologies for utilizing resources in space will contribute to both sustainable space exploration as well as sustainable terrestrial mining practices. Space resource utilization, or SRU for short, refers to the exploration, planning, mineral processing, metallurgical processing, and sale of resources in space. SRU has been a point of interest and study for the space community for approximately 60 years. However, it is only been within the past few years that SRU has begun to transition from an idea to reality. Let's now Thorium and uranium are useful for large-scale power systems, as well as rare earth elements, potassium and phosphorus, necessary for the semiconductor industry. Titanium is available for the manufacturing of strong, light fuel. And last, potentially billions of tons of water, useful for producing rocket fuel, sustaining astronauts via life support, energy storage, hydroponic farming, and more. As of 2016, the United Launch Alliance in the United States confirmed that they would be willing to pay up to $3,000 per kilogram of fuel, namely oxygen, hydrogen, or both, made available to them in low Earth orbit, or up to $500 per kilogram on the surface of the Moon. This announcement was quite historic, as it was the first time in human history that a standing order has been placed for a commodity produced somewhere other than on Earth. The first target for SRU is to produce fuel in space. This can be accomplished through the extraction and electrolysis of water ice at the poles, or through the electrochemical reduction of oxygen-bearing minerals. To quantify the financial benefit of SRU, a recent report produced by the Government of Luxembourg and PwC found that space resources could realize market revenues of up to $190 billion, as well as produce efficiency gains and spillover revenues, each worth up to $150 billion by 2045. This tracks well with predictions about the overall growth of the space sector made by Bank of America Merrill Lynch and Morgan Stanley, both of whom predict the space sector as a whole will be worth over $1 trillion by 2040. We have now established that the Moon is an ideal destination for SRU. So I would like to move on to discuss the work that our research group at Imperial is doing to help make SRU into a reality. Here you can see the lunar mining flowsheet that was developed by the European Space Agency's SRU topical team, led by my supervisor, Dr. Catherine Hadlett. As with a typical terrestrial mining operation, we have three broad stages. Excavation and haulage, whereby our run-of-moon material is initially collected. Beneficiation, where the as-mined material is crushed, sized, and enriched. And extraction, where we are able to produce the desired end products, such as pure and alloyed metals, oxygen, fuel, and other volatiles. Our group is focused on the beneficiation stage, specifically on the sizing and enrichment steps. Why do we need to beneficiate? Well, much as on Earth, naturally occurring homogeneous deposits of desirable minerals, pre-sized, sorted, and ready to go, are not available on the surface of the Moon. Furthermore, not all of the minerals that are present are equally suited to oxygen production. One material that is of particular interest to SRU is an iron titanium oxygen-bearing mineral known as ilmenite that is found in the dark gray Mare regions on the Moon. Ilmenite is attractive for early SRU operations as it can be reduced with hydrogen at relatively low temperatures. Some hydrogen reduction systems, however, require ilmenite concentrations in excess of 80% by mass and for the feed to be sized optimally. Clearly, such a feed would not exist naturally on the surface of the Moon. Hence, a beneficiation process would be necessary to produce it. Furthermore, beneficiation must be considered in order to maximize confidence in an SRU operation's ability to meet a given demand. The image on the left shows the relationship between the mining rate and the reduction step feed rate versus the grade of ilmenite contained within the regolith. The mining rate increases linearly, while the reduction step feed rate decreases linearly since the oxygen yield is correlated to the ilmenite content. What this implies is that reducing the reduction step feed rate by increasing the content of ilmenite will result in an overall increase in the mine rate. We then considered a theoretical lunar mine with an annual demand of 1,000 kilograms of oxygen. A statistical estimation of the confidence levels in the mining and reduction feed rates required to meet this demand was performed using a Monte Carlo simulation, the results of which are found on the right. The parameters varied in the simulation were particle size, agglutinate decontamination, operational availability, and oxygen yield. After running the simulation 10,000 times, my supervisor, Professor Jan Silliers, found that it was a mining rate in excess of 60 kilograms per hour that would be required in order to have 90% confidence of meeting the annual target. This rate is 10 times higher than the estimates made previously that did not consider the regolith variability or beneficiation steps. Clearly, beneficiation must be addressed in future SRU operations. So what are we doing about this? Well, our research group has two main focus areas. The first is on the development of dry beneficiation technologies for use on the lunar surface. Dry methods are necessary for use on the moon due to environmental constraints and a lack of flowing water. Here you can see the experimental rig that I designed and built. It employs a process known as triboelectrification, whereby individual mineral particles gain either positive or negative charge through repeated contacts with surfaces or other particles. The magnitude and polarity of the acquired charge is a mineral-dependent surface property that is then used to perform separations by mineral type, using strong electrostatic fields. The plots that you see on the right show some of the results from my initial single material characterization tests. Here, I used a simple vibrating copper pipe as a simple tribocharger and 5 different electrostatic field strengths to characterize the charging and freefall motion of ballotini and crushed ilmenite. These initial tests found that the particles did acquire sufficient charge to have their motion affected by the electrostatic field. However, the tribocharger itself requires further optimization in order to increase the proportion of particles that acquire sufficient, meaningful charge to be affected by the electrostatic fields. The second focus that our group has is understanding the underlying physics that governs the tribocharging process. While tribocharging itself has been known and observed for thousands of years, the actual mechanism that drives it is poorly understood. This work is a focus area of my fellow PhD student and co-author, Ruben Cruz. The image on the left shows the temperature and humidity-controlled glove box used to perform saturation charging experiments. The plot on the right shows how the specific charge of PTFE, PVC, and LDPE particles vary with respect to particle radii. While larger particles acquire greater absolute charge than smaller ones, the charge per kilogram of smaller particles is appreciably higher. This result has a direct impact on my own research, as it indicates that smaller, lower mass particles should interact more strongly with an electrostatic field relative to larger, more massive ones, thus improving separation characteristics. Many of you may be wondering how our research can be beneficial for terrestrial mining operations. Well, traditional wet mineral processing methods, such as froth flotation, are highly efficient, but they are very expensive to deploy, especially in water risk areas like the Australian outback or sub-Saharan Africa. Since we cannot consider wet methods for use on the moon, we are forced to develop and mature effective, reliable, and resilient dry methods for a demanding and remote environment. By proving these technologies in space, it will hopefully help to build confidence on the part of the terrestrial mining sector to consider replacing wet mineral processing techniques with dry ones. This shift could potentially save hundreds of millions of tons of fresh water each year, as it will also help to reduce mine capex, opex, and impact on the environment. In conclusion, space resource utilization is coming and will likely be demonstrated by the end of this decade on the moon. SRU will be critical for the establishment of a permanent human presence on the lunar surface, as well as for establishing and enabling longer duration human spaceflight missions to more distant targets such as Mars. Furthermore, the subsequent SRU economy that emerges will offer traditionally terrestrial industries the opportunity to break out beyond the silo of Earth. Beneficiation will be an integral part of the SRU flowsheet. Given the restrictions imposed by the lunar environment, reliable and effective dry beneficiation systems will be developed and matured out of necessity. Triboelectrification and freefall separation have shown promise for this application. However, there is still work to be done to understand the underlying mechanisms and to optimize the charging process itself. Finally, once these techniques have been demonstrated on the moon, spin-offs will offer terrestrial miners an effective enrichment method, both with lower operational costs and environmental impact. If you're interested in further reading, you can find the resources mentioned throughout this presentation here. And with that, I'd like to thank you for your attention, as well as to thank Imperial College, the Luxembourg National Research Fund, the European Space Agency, and the Natural Sciences and Engineering Research Council of Canada for their support of our research. Thank you again.
Wow, what an interesting presentation.
Hi,
and this definitely fits the theme of novel approaches to mining. My only hope is that we take all of the lessons that we have learned about sustainable resource exploitation here on Earth and apply it to the extraterrestrial bodies. Thank you so much for that presentation, Joshua. Our next presentation, which you sort of heard only the beginning clips of, apologies, and I'll also just like to apologize for the sound issues that we had in the previous presentation. We will ensure that things work smoothly from now on. But our next presentation is from Daniel Hastings from the University of Queensland, Australia, with the title, Incorporating Environmental, Social, and Governance Factors in Strategic Mine Planning. Ladies and gentlemen, I will repeat, Incorporating Environmental, Social, and Governance Factors in Strategic Mine Planning. Please enjoy.
Hi, my name is Daniel Hastings and I'm undertaking a higher degree by research at the University of Queensland on the incorporating of ESG factors in strategic mine planning. ESG issues in mining is becoming more and more important, not just for ESG outcomes themselves, but also for the potential future impact on supply and the ensuing ramifications on society. Industry and business know that ESG factors in mining is a problem and it's only getting bigger. It is suggested that current strategic mine planning systems are unable to adequately include ESG factors, which presents a significant problem. Additional to the less than optimal ESG outcomes from operations, if inclusion of ESG factors in planning systems is not addressed, the resulting lack of ability to provide development options for projects that minimises negative ESG outcomes may lead to a supply-side crunch that will result in the rapid development of many projects that have significant ESG issues. Mining is seen by a large portion of society as environmentally and socially irresponsible and destructive. We accept that mining activities impact the environment and the community in negative ways, but it is also important to acknowledge that mining is a fundamental requirement for our civilization and has many positive impacts. Daniel Franks captured this sentiment when he wrote that with every transaction, society affirms its reliance and its lust for the products of the mineral sector, but with every word, it restates its displeasure at the way that these products were produced. Nothing has really changed in a meaningful way since these shortcomings have been identified. Mining is trying to respond, but it is suggested that they are really struggling to include ESG factors in current planning practices. Too often, mining discussions are simplified into a choice between mining or protecting the environment and community. The mining industry must endeavour to show that this is not an or statement, it needs to be an and statement. Current approaches to ESG issues in mining is reactive. Projects are designed, then appraised for ESG issues. We need to be proactive in development design. A large dislocation exists between intent and outcome when assessing ESG issues in mining development options. These current analyses occur at the beginning of the project and at the end, but not throughout the life of the project, and are generally not included in strategic planning, certainly not in any significantly integrated way. This reactive view also precludes the idea that improved ESG outcomes are possible while maintaining corporate economic requirements through better strategic planning systems that seek to include ESG issues. So why is there no robust and comprehensive framework for this to occur? Well, at its core, inputs are the problem for current mine planning systems. Quantitative inputs are a lot easier to handle than qualitative inputs, and ESG issues quite often qualitative in nature. Strategic mine planning involves primarily pit and schedule optimizations that solve to an objective function, which is almost exclusively NPV maximisation. So using current strategic planning systems, qualitative ESG variables need to be converted to economic values. Currently, willingness to pay is the primary method for deriving quantitative economic values for qualitative ESG variables. This method has been around for over 55 years, and as of 2011, more than 7,500 contingent valuation studies and papers have been undertaken. It does, however, have many shortcomings and biases. Who is doing the assessment and who is gaining the benefits? The challenge is to get both quantitative and qualitative ESG variables into the strategic mine planning framework. To achieve this, there must necessarily be a linkage between mining activities, which can be measured and forecast as part of the mine development plan, and qualitative ESG outcomes. The key will be to show that linkages can be made between quantitative mine development outputs and qualitative responses. So as to avoid issues with economic valuation, the aim is to provide a framework that utilises non-economic metrics that can then be included in scenario analysis. Since this methodology involves both financial and non-financial metrics, the current optimisation processes cannot be the only ones used. Additional processes will need to be added to the overall planning system. If the objective function of the optimisation process is changed from maximising NPV, then the optimisation becomes flawed. Multiple objective functions are undertaken, and this can cause conflict which results in poorer performance. You can mix financial metrics and probability, but mixing financial and non-financial metrics in the objective function will result in opaque outcomes. Apart from discount rate, risk is not typically incorporated into NPV in mining applications. Work on this is currently being done, however, the incorporation of qualitative risk presents additional issues. What could an ESG cognizant planning system look like? The current strategic planning process is shown in orange. Mining inputs comprise of various models, design criteria, and financial metrics. Some of these inputs flow directly to the optimisation processes, such as geotechnical and haulage models. However, a lot of the information is used to develop a geomet model that carries data required to determine ranking metrics, i.e. cash flow grades. The optimisation process commonly comprises of pit optimisations using an LG or pseudoflow algorithm to determine the optimal pit shell. Mine design processes follow when mine stage and other detailed design is done. This enables the creation of material bins to be calculated for use in the schedule optimisation. Schedule optimisation, normally using mixed integer linear programming, dynamic programming, or both, can then be done to derive the optimal period schedule based on the objective function, that being maximisation of NPV. Most normally, quantitative ESG inputs can be included in this process. At this stage, these ESG inputs are pretty much only waste management costs. Once the schedule optimisation is complete, the output is passed to a corporate financial model to enable inclusion of financial activities such as depreciation and amortization, company taxes, movements in stock and working capital, and other such things. One possible solution for inclusion of ESG variables is shown in green. That is the creation of a geo-ESG model and system dynamics modelling. The geo-ESG model will carry any quantitative and possibly some qualitative information that can be estimated and tied back to the underlying geological model. These variables will be carried through the current optimisation process, but not necessarily inform the current process. This is done so as to provide the ESG variables in period format that can then be fed to the system dynamics model from both the financial model and directly from the schedule optimisation. ESG variables from the geo-ESG model will also likely be input directly to the system dynamics model. The system dynamics model will provide the framework by which quantitative period variables are linked to qualitative variables over time. The framework will provide for the use of modules that can be built for any ESG variable of interest or ESG variable determined to be impacted by the mining development. These modules will be different for each operation as a result of things such as mine geographic location, commodity type, local, regional and national community makeup, cultural considerations, surrounding natural environment, etc. These variables and linkages can be mapped temporally in the system dynamics model, including well beyond the actual life of mine. The ESG variable period output data could be combined into a single metric like MPV is, or other metrics could include the schedule maximum or some inflated or discounted outcome. These outputs, whatever form they ultimately take, can then be used to undertake ESG cognizant scenario analysis. If the processes are set up correctly, it becomes amenable to a brute force assault, whereby a very large number of scenarios can be executed in a relatively short time frame to build a database of possible outcomes. Scenario analysis can then be undertaken. Ideally, identification of scenario pairs that have similar economic outcomes but vastly different ESG outcomes would be done. Drilling down into the data would allow for determining which development options impact the ESG outcome variance most. Decision makers would then be able to take ESG impacts into consideration when determining development options by being better informed of the likely ESG outcomes of each scenario. Thank you.
Another interesting presentation. It is nice to see the incorporation of environmental, social, and governing factors alongside financial models when designing decision-making algorithms for the mining industry. Thank you so much for that presentation, Daniel. Our next presentation is from Flav Andre, who is based at the University of Queensland, Australia, with the title, Developing a Continuous HVP System for Mining Operations. Developing a continuous HVP system for mining operations. Ladies and gentlemen, please enjoy Flav Andre's video.
My name is Flav Andre, and today I'm going to present my work that has been developed here at GJKRMC at the University of Queensland, alongside Dr. Christian Antonio and Professor Frank Shi. And the name of this work is Developing a Continuous HVP System for Mining Operations. Starting with a quick introduction, we all may be aware of the current scenario in the mining industry, where there is a constant increase in the amount of material that is being processed in mining operations. That's caused basically because of two major factors. First of these factors is that high-grade deposits have been depleted over the years, and the grade of existing deposits is declining. We can see on the image on the left that for a few minerals in Australia, all of them present the same decreased trend. The second factor is increased demand for metals by our society. In the case of copper ore, for example, in the image on the right, the production rate is increasing at approximately 3% per year. The decline of our grades and more material being processed by mining operations means that more energy is needed to maintain similar levels of metal production. The high voltage pulse technology is a promising technology that can mitigate these problems. Studies so far have demonstrated that the HVP can improve the liberation of valuable minerals, reduce the resistance of the ore to breakage, and also discriminate particles according to their mineralization. That will come with the possibility of feeding your system with a higher grade ore, and also reduce the consumption of your plants. And you can also operate your plant in a smaller size and develop new circuit options, including the HVP. However, most of the studies so far have been done in bad test methods, using, for example, the self-frag machine, as shown in the image. And to be used for mining operations, the HVP must be converted to a full-scale continuous operation that is able to treat large tonnage rates. The high voltage pulse is characterized by a fast rising pulse that is applied to the solids. The energy of this pulse is stored in capacitors over the time and is discharged fastly by the electrons. The discharge path will happen through the material with weaker breakdown strength. And the breakdown strength is influenced by how fast the electric pulse rises. We can see on the image that if the pulse rise time is shorter than 500 nanoseconds, the breakdown strength of the rock will be smaller than the breakdown strength of the water, but it will be larger than the breakdown strength of the air. And that's the reason why HVP processing must take place underwater. If the device time is of around 500 nanoseconds, then the likelihood of the discharge happening through the water or through the particle would be quite equivalent. Studies in HVP applied to the mineral industry started around 50 years ago, but at that time the system was used for rock breakage and the energy consumption was too high. Because of that, researchers then draw their attention to other applications, such as the enhanced mineral liberation promoted by the HVP. In comparison to mechanical crushing methods, the HVP can deliver better liberation performance at large size fractions. This leads to the possibility for early recovery of those coarse minerals. However, this application consumes a lot of energy, so it's only feasible for a few specific cases. The liberation happens due to the formation of a tree-like discharge within the particles at the boundary of those elements. Another application for the HVP is the pre-weakening, that is characterized by the decreased hardness of ore after HVP treatment. And that happens due to the formation of microcracks within the particles. And this allows the possibility of energy savings on downstream process. And another important thing about the pre-weakening is that only the particles that contain the minerals will be weakened. And those particles that are contained basically by gangue will remain with the original core. Perhaps one of the most important applications for the HVP is the selective breakage, because it unleashes the possibility of using the HVP for ore preconcentration. And that happens because the HVP is able to target particles according to their mineralization. And you can just reject the waste using a screening stage. So if you process your sample with the HVP, and then after screening, you can divide your sample into a low-grade coarse product and a high-grade fine product. And the good part of using the HVP for a selective breakage is that it doesn't consume a lot of energy, and the selective pre-weakening will also take place. A few attempts have been made to operate the HVP continuously. And all those attempts, they rely on belts to transport the material within the processing chamber. We can see in the image two different devices that were developed by Cellfrac. And the problem with this system is that because they rely on belts to transport the particles, and the lower throughput will require the parallelization of several machines to achieve the required throughputs by mining operations. And that will come with a high cost. A different approach to treat particles using HVP was proposed by researchers at the JKMRC and submitted for patent. It consists of a new electrode design that dispenses the use of belts. And its difference is because the new design is able to classify particles instantaneously and therefore optimize the amount of energy used to treat each particle. This project will develop a laboratory scale HVP continuous system that is being composed by a feeder system that will feed the material into the processing zone, and the system will collect the material according to their grade at the end of after processing. There are a few requirements that we must meet before developing the system, such as the particles must be presented evenly to the processing zone, and also that it must be suitable to test different size fractions, and also it has to be flexible enough to test different arrangements of the system. The collection of the material must be done in two different points according to the department during processing, and most important, the system must be able to operate underwater. So this is the proposed laboratory scale HVP system, and it will be the first step to implement HVP mining operations. And it will allow us to understand how to operate this novel approach and measure the benefits of implementing the system in a mining operation. This will allow us to develop new circuit options using the HVP, and that will also serve as a base case for future pilot scale HVP plants. I would like to acknowledge the support of the HVP Collaborative Research Program that is composed by Newcrest, Newmont, and Complex Ore Body, and also the support of the Huazhong University of Science and Technology and the University of Business. Thank you very much.
Thank you so much, Flavio, for that presentation. I definitely wish you great success in your attempts to scale up the HVP system. Now, ladies and gentlemen, that brings us to the very end of our first session for day one, which was the novel approaches to mining. I would like to just remind the audience to please make use of the Q&A function if you have any questions. And as I said, we will try our very best to make sure that they're answered. So to run the very first Q&A session, I would like to call to the virtual floor, Catherine Edward. So Catherine, please take it away.
Great, thank you, Michael. So if anyone has any questions that we can direct towards the student presenters, please pop them in the Q&A and we can get the show on the road. Okay, so the first question goes to Joshua. And the question is, what do you envisage the next steps of your research to be, and when do you expect commercial lunar mining to become a reality?
Yeah, those are very good questions. So thank you again for everyone for having me here. So to answer the first question, the next stage for my research is to improve the design of the triboelectric charger that we use to charge the minerals for separation. So to address that, I've moved on to some computational research whereby I'm using discrete element modeling software to simulate the charging process so that we can optimize the charger design to be more efficient for separations. As for the second question, when will lunar mining and space mining in general be more of an economic entity? That's a bit of a harder question to ask. I would say probably there'll be demonstrations of the technology by space agencies and possibly by private companies, definitely by the end of this decade. But as for the industry itself, that we think is, or I think will probably be in the early to mid part of the next decade. So 2030 to 2035, I think will be when we start seeing some of the initial actors moving into space mining and to actually seeing profit from those types of endeavors.
Awesome, thanks so much, Joshua. It's really amazing to think that it feels like not so long ago we were all getting excited about sending someone to the moon just to walk on it, and now we're thinking about mining there, so it's really great. Thank you. The next question I have is for Flavio, and it is it ever going to technically be feasible to conduct HPV dry? And you mentioned the time rise was critical to this.
So thank you very much for the question. It's a pleasure to be here. So it is possible to conduct it dry. There are a few tests happening in a few different places to apply some chemicals to the particles so they can conduct the pulse without submerging them into water. So that's a possibility. And I couldn't get the second question.
It was just a comment saying that you said the rise time was critical to that.
Oh yeah, so that's quite important. So because when you're operating the HEP, so if you have a post time rise that is too long, then it will probably go to the air, in this case, or the water. So yeah, it's quite important to have a short time rise, but the technology nowadays is able to provide that to us.
Okay, awesome. Thank you for that. I'm going to pass on a question to Daniel Hastings. And the question is, what scale of mining are you targeting with this ESG framework? Is it traditional LSM or ASM or small scale technology mining? Daniel? Okay, I will post that in the chat. I have another question for Joshua. And the question is, who will have rights for lunar mining?
That's also a very good question, and is something that we don't really have a definitive answer for right now. So the United States recently set out the Artemis Accords, which outline sort of the initial use of minerals in space. And they do have some, as far as I understand, there is some verbiage in there that discusses ownership rights. However, the international legal community is still a little bit unsure of exactly kind of how ownership rights will ultimately work. There are some ideas for early missions to try to test these laws to see sort of what will happen if say, NASA were to buy some either just unprocessed regolith from a commercial entity, just to sort of see what happens with regards to the law. But at present, there's still a lot of kind of open and unanswered questions in this particular area. But this is something that we hope will kind of be spurred on by the US's plans to return to the moon in the next decade. And I think that will have a huge impact on the legal community to start really considering these questions in earnest.
Okay, cool. Thank you. I have one more question for you, actually, Joshua, to follow up on that. And it was, how do we go about doing exploration to define mineral resources on the moon? And will we follow the same codes as for terrestrial resources?
Okay. Both also very interesting questions. So the first part, to actually identify mineral resources on the moon, it will be somewhat similar to what we would do on Earth, but we would rely more heavily, initially at least, on remote sensing technologies to sort of kind of guide where we would ultimately send the first sort of landed missions to do some ground truthing and in situ measurements of I guess, resource quantities. That would be how we would start to initially characterize in greater detail where we would like to begin extracting resources for the production of fuel or any other commodities that we're interested in. And sorry, could you just repeat the second question? Oh, the codes and for reporting. So there's actually some work going on right now in Luxembourg to define a similar set of codes to JORC, but for the moon instead. This framework is called LORS, and it's been in development in conjunction with the University of Luxembourg and the University of New South Wales, and is sponsored by iSpace Europe in Luxembourg. And so this has been some of the first developments of reporting standards for space resources, and it's being developed by Dr. Carlos Espejel. So if you would like to find more information on that, feel free to get in touch with me on LinkedIn or another platform, and I'm maybe happy to pass along more details on the reporting standards themselves.
Okay, awesome. Thank you so much, Joshua, for that. I have another question for Flavio, and it's on the high voltage pulse. So does the current energy transition to renewable technologies and the potential reduction in energy costs advantage or disadvantage HPV applications?
So could you repeat that? Sorry, I couldn't get the beginning of the question.
So the current energy transition to renewable technologies and the potential reduction in energy costs, does that advantage or disadvantage HPV applications?
It's obviously, it's possible to, it's a great advantage because it's a technique that consumes a bit of energy, but with the use of the HVP, we expect it to reduce the energy that's being consumed in processing plants. So you can, with the transition to the renewable energy, you can even maximize our savings with this.
Oh, okay, cool. All right, so I'm going to close out this Q&A session. If anybody has any more questions for the presenters, please feel free to contact them via email. You'll see their contact information is actually on the ebook of abstracts that's going to be published. Well, it's published already on LinkedIn, so just have a look through that. And thank you so much, everyone, for participating. This was really great. I'll hand it back over to Michael.
Thank you so much, Catherine. That was actually really quite informative, and it's quite nice to hear the level of thought that goes into these projects. And I hope that our audience will also keep engaging with us even after the showcase is done, because we will be posting videos to YouTube. So please do not fret if you missed the video or you would like to rewatch it, we are going to give you opportunities to do that. So you can find the links and you can actually watch the videos and all of that. So yeah, that wraps up our very first session. What we are going to do now is actually go to an even more exciting session, and that is our very first panel discussion. I would like to tell you about it, but there is another committee member that will definitely sort of wring my neck if I do that. So I'm going to actually pass over to him, and that is Mr. Nick Bilham. So Nick, please do take the floor.
Great, thank you very much, Michael. So yes, we have a fantastic discussion session coming up now, following on from those 3 talks, which were about very different stages of the mining life cycle. And we wanted to group them together, although they were quite different, because of thinking about different sorts of innovation and different ways of thinking about doing mining differently across the mining life cycle and across different sectors of mining. And so there's a number of other presentations on that topic as well, which are on the YouTube channel. So do go and check those out. As Michael said at the beginning, we're only able to show a limited number of the fantastic presentations that we had in. And we wanted to think about this idea of joining up of innovation across the mining life cycle in line with our topic of breaking silos. So we have 3 panelists joining us. I'm delighted to introduce them to you. We're joined by Jeremy Hanhinyemi, who's the Technology and Innovation Manager at Weir Minerals, one of our generous sponsors. We have Dr. Karen Hudson-Edwards, who is a Professor of Sustainable Mining at the Camborne School of Mines and the Environment and Sustainability Institute at the University of Exeter. And we have Dr. Catherine Goodenough, who is a Principal Geoscientist at the British Geological Survey. And I think that they are all online with us now. And first of all, I'm going to ask Jeremy Hanhinyemi to speak briefly about his company, Weir Minerals, as one of our sponsors for the event. And after that, in about 5 minutes or so, we'll go into a general discussion about innovation in mining and how we can view that in a broad, holistic way across the life cycle. So, Jeremy, over to you.
Thank you, Nick. I'll just share my screen. So hopefully that's coming across okay there, Nick.
We can see you, thank you. We can see your slide.
Excellent. So it's my pleasure to represent Weir today and to be joining you in the Next Gen Resources Student Conference. I thought I'd introduce a little bit about Weir. So Weir is one of the largest global engineering businesses. It was established in the late 19th century by George and James Weir. Today it has approximately 15,000 staff and annual revenues of about £2.5 billion. This illustrates a little bit about our operations around the globe. So you can see we have facilities in more than 70 countries. I thought I'd speak a little bit about what we do as a business. So we look at mission critical solutions. We focus on highly engineered equipment, intensive aftermarket care, and also emphasize comprehensive global support. So here at the Next Gen Conference, we've heard a lot about the challenges around environment and sustainability within our industry. We recognise that some of these challenges will include mass urbanisation, carbon transition. We've seen reductions in head grade discussed in some earlier presentations, and increasing demand. We believe an important part of these technical challenges will be innovation in engineering within the mining sector, and that's how we believe Weir can make a difference. A little bit about what we do. So we're focused on the extraction, materials handling, comminution, and the mill circuit and concentration parts of the mining value stream. Some of our core divisions are in minerals and also in ESCO. This provides a bit of an overview of what we do as a business. So you can see in terms of the extraction, we've got ESCO on the left and its ground engagement technology, through to Trio, plant solutions and crushing and grinding equipment. Moving through the flow sheet, you can see that we're involved in slurry transportation with brands such as Warman and Linatex and valves. We also work across the classification and screening parts of the flow sheet also with Trio, Enduron, Cavex, Linatex and other brands as well. We do a lot of wear lining and corrosion protection services, and we also support in tailings disposal with products such as Geo and also in mine dewatering and water management. We have a series of world-leading brands and which provide very high-performance equipment, and some of these are listed here. You can see, you know, some of the brand stack, varying from Warman slurry pumps right through to Enduron HP GRs. So looking forward to seeing the great presentations, and thanks for providing me an opportunity to talk a little bit about Weir, the sponsor for one of the sponsors for this conference. Thanks, Nick.
Great, thank you very much, Jeremy. So thank you, stopped sharing, and we can now move into the discussion. So thank you very much, Jeremy, Karen and Catherine, for joining us. And as I said, we've heard these three quite varied talks so far on planning, so the very beginning of the life cycle. On the processing stage, we've heard about mining on the moon. And then later in this session, in this showcase, we're going to be hearing presentations on waste and tailings and on mine closure. So we're really thinking about the whole life cycle of the mine across the morning. So thinking back to those presentations and forward to the ones we're going to be coming to, I wondered if you had thoughts about what challenges there are and what opportunities there are for sustainable innovation across the mining life cycle, and for joining up those innovations, for making sure those different stages work well together. So Karen, I don't know whether you wanted to comment first.
Thanks, Nick, and thanks very much for the invitation to come along and speak today. I must say I've really enjoyed the presentations. I've seen the ones this morning and a couple online, and want to really congratulate everybody. It's a really professional and great conference, so thank you. I've got a huge list, but I will only sort of touch on a couple to begin with. I think the innovation is really coming along really well. We're seeing robotics used a lot more. We're talking about mining on the moon. But some of the challenges I see with getting the innovation used is, first of all, the social side of things, getting acceptance for mining in the first place. So we all know that social license to operate is a big thing that companies are starting to address, but I think there's a lot more that can be done in that space, particularly with getting acceptance with the negative aspects of mining that have happened in the past. So the innovation is there and we're ready to use it, but I think we really need to be engaging with communities and making sure we're covering that social aspect. And the second thing is thinking about the talk that talked about, I think it was Sage who's going to talk after in the second session, talking about the fact that the ore grades are going down and we're having to think about mining either smaller high-grade deposits or deposits with lower grade. So I think it's how innovation can address those two challenges is a topic that I'd like to bring up. Thanks.
Yeah, very important questions. So Catherine, why don't you go next?
Thanks, Nick, and morning everybody. And I'll second Karen's comments on really interesting talks so far. So thank you to everyone who's been speaking. I'm from the British Geological Survey, and I'm a kind of classic geologist, if you like. So I go out and hit rocks with a hammer, or at least I would if we were allowed to at the moment. And I'm very interested in innovation right from the start of the life cycle when it comes to exploration, one of the things that really interests us at BGS in terms of sustainable mining is access to data, making sure that in all countries, the data that are needed, the geological data that are essential for exploration, are available to the people who need them. That might be governments, it might be civil society, that kind of thing. It might not just be the companies that are actually doing the exploration. And I think that underpins a lot of sustainability. If you have good background data about the resources that are there, about the communities that live around those resources, about the environment, then you can use that to start understanding the whole life cycle. And I would very much echo what somebody's already said, that mining is essential. Sustainable mining has got to be part of our future, because we can't have, you know, the lifestyles that we want without sustainable mining. And I think we need to make sure that at every step of that life cycle, we have the information and data we need, and we make it available to all the people who need it. That's definitely part of our work at BGS. Nick, I'll hand back to you.
Thank you very much, Catherine. And Jeremy, what any initial thoughts from you on this, on these challenges and opportunities for innovation in that broader sense as well that Catherine and Karen are both talking about?
Yeah, yes, indeed. I think that within our industry, there seems to be a challenge for us to accelerate the uptake of innovations available to us. There seems to be a relatively long cycle between the, when new technologies are identified and proven in a lab environment in terms of, their benefits for the wider industry, and then to eventually see them brought up to industrial scale and implemented broadly within the industry. There's quite a long time scale associated with that. I'd like to understand that more and what we could do to tackle that. I think that there's a proliferation of issues that go along with it, such as the fact that our industry requires capital intensive equipment, and there's quite a lot of risk associated with implementing new technologies. I think that's part of the challenge. I think also it would be my observation that there's relatively few trained professionals working in these in these disciplines, that are required in order to implement this technology, develop it, and also implement it, industrially. So I think the importance of, and I think that's probably something to consider, given this is a student conference as well, that the vital importance of training the next generation of minerals and mining professionals to implement these research and development and grow the research and development initiatives longer term to support the sustainability and environmental performance of our industry is vitally important. So that'd be a couple observations from me.
Absolutely. And in the past, I've often heard it said that with the very long timescale for developing mining projects and a degree of maybe conservatism in some parts of the sector and a sort of slowness to move and to change, these issues you're talking about of investing in skills and people, and also of investing in R&D and the whole R&D cycle becomes really important. That's not a sort of contingent matter that comes and goes depending on the state of the resource cycle at that point. You talked about risk as well. So I wonder whether you and the other panelists had thoughts on whether that's being done in the right way at the minute. I mean, is there a recognition that there's a need for continuous investment in R&D and in people, and to have a more sort of innovative mindset? Or is there still a risk of being stuck in rather traditional ways of doing things and just really changing at the margins?
I think, Nick, if I could just step in on that, I think it is a really interesting point that individual companies, obviously like we are in many cases really innovating and really investing in people, but obviously that can be quite sort of individual to those companies and perhaps to the regions that they're working in, for example. And certainly one of the issues that we do face is demonstrating to governments that actually we really need to be funding, as you say, more training in this area, more research, more to fit around that resource cycle. And it is certainly one of the challenges, I think, is about communication. Somebody put it across very well, and I think it was the second talk we heard earlier, the fact that people want more and more products from mining, more and more technology, but yet they're still against mining so often as a concept. And somehow getting across that communication to the wider public, to governments, into the media, the fact that if you want your mobile phones and you want your nice cars, your electric vehicles, and you want nice houses, really, you're going to have to deal with the fact that mining is essential to all of that. So there's something there for all of us involved in this conference today to think about how better to communicate that to all of the different stakeholders that are out there.
Absolutely. Yeah. Karen, any thoughts on that?
Yes, my comment follows exactly on from that. And we see this at the Camborne School of Mines. So we run, of course, a geology and mining degrees, both at undergrad and postgrad level. And while there's still a lot of interest, I think we still struggle with trying to get students interested in mining, interestingly. And I think maybe that's perception of how bad mining could be and the negative impacts and the sort of NIMBY, I don't want to mine in my backyard idea. So I think it's up to us to communicate and get across how exciting a career in geology can be, why it's important, that we need people, that there are jobs out there, and getting it down to the early students coming through our schools, even before they get on to later levels. So the more we can do about communicating our science, the prospect of mining the moon, using robotics in mining, and just doing mining or geology out in the great outdoors, I think is really important for us.
And that side of communications and trying to bring, to make it clear that mining's a space that people should think about going into, that it's an exciting place to work where you can be contributing to sustainable development, goes hand in hand with what you were talking about earlier, Karen, the need for addressing issues around social acceptance and for the innovation and the research to include that space as well. So
Absolutely.
that potentially there's a win-win in terms of if you can get that engagement with communities, with governments, with civil society better, that it might help on both fronts. But it's challenging, and I wonder whether you had thoughts about where we should be going and where the weaknesses are and where the gaps are there at the minute, who we should be working with. Are we working with the right other disciplines?
Well, I think there's a lot more effort being made to work across disciplines in all aspects of mining, both within geology departments, like ours at Camborne School of Mines, but actually across universities, across disciplines. And that's not just in academia, it's getting out, working with companies, working with government, working with other institutions. Yet I think there's still a lot more to be done. On the sort of public front, I think we could work with, we work within the social media, but working with news organizations, documentary makers, getting more people out there to be the face of mining and geology, a bit like a David Attenborough for mining and geology would be wonderful. That's going to capture the public's attention, and I think probably more can be done in that space, definitely. So how we do that, engaging with our science communication departments, talking to media people, I think it sounds a bit, popular, but that's what we need to do to really get our message across. I think that would really help.
Absolutely. Jeremy, how do you view this from your company perspective? We're talking about engaging with all sorts of different audiences now here, but it's fundamental to how mining is seen and to potentially how it develops in future.
Yeah, it was very interesting listening to Catherine and Karen there. And in terms of the need to market ourselves in our industry for the important work that we do, and also to attract talented people into the industry to solve these big challenging problems. I think that's true. I think there is a big piece we need to do there, and I think that, you know, we do need to communicate more clearly about the nuances we have between growing new minerals and metal extraction and, you know, and other commodities, you know, versus all the challenges we have from you know, sustainability and point of view. I think in terms of, you know, look, speaking from a supplier perspective, part of the, you know, challenges that we have was in order to implement the innovations we have, we do need to work more closely with the end user of those innovations. And I think more collaboration between suppliers and, you know, industry and users and mining firms, I think would be particularly if it was, you know, the more open and the collaboration, I think the better, you know, partnerships. And that's what we're really seeking here, to get as close to our customers as possible to understand their challenges. And some of those, you know, touched on today, but I think that becomes important for supply organisations.
Okay, thank you. I was getting a bit of interference on your sound there. I don't know whether, yes, I think we got bits of that, Jeremy. I might come back to you in a minute. Your sound was a bit unstable there. Catherine, did you want to add anything in terms of this, thinking about who we're working with, not necessarily just in terms of engaging the public and so on, but this broader challenge of thinking about where we're going with mining, its sustainability, its role in sustainability, and that perception piece?
I think one of the really interesting points, Nick, is the group of people from different countries that are involved in organising this conference. Because, of course, in Australia, mining is a very well recognised industry. It's very well regulated. I've spent a little bit of time on an Australian gold mine. I've been incredibly impressed with how it's run. And I think in Australia, you know, mining is quite well recognised as a really important industry, and one that is doing its best to be as sustainable as possible in most cases. Here in the UK, the situation is a bit different because, as Karen pointed out, we have the NIMBY issue, except for maybe in Cornwall. Elsewhere in the UK, mining, except for coal mining in the past, isn't really something that's recognised as being that important. And so a lot of people don't understand the importance of it. And so we have very different challenges in kind of getting across sustainability issues here. And then I do a lot of work in various African countries, not so much in South Africa, but in various other African countries. And of course, mining is tremendously important. Artisanal mining is often a major source of livelihoods. But there are other major concerns there. Many governments want to have big mining companies coming in, but actually a lot of people are getting their livelihoods from artisanal mining, and regulation of that and support for those artisanal miners can be really varied. So the way we need to address sustainability is actually quite different across these different countries, and innovation can be different in different places. You know, innovation, fantastic technological innovation in processing in Australia might be the equivalent of a furnace to make sure that you can get mercury out of the gold mining process in Ghana, for example. And we need to be looking at all those different aspects of innovation and sustainability, and also finding a way to bring, you know, new information, new processes from countries like Australia to be applied in other countries like the UK, perhaps, where we don't have such a well-developed mining industry. So I think this global approach of this conference is exactly one of the key things we have to be thinking about.
Absolutely, and we have student presenters from 4 continents in the showcases. We have from a 5th continent on the YouTube channel as well. But of course, the projects that they refer to are all over the world. And specifically, you talk about ASM. We've got a session, excuse me, a session on ASM in the 2nd showcase session, which I encourage people to tune into, where again, innovation in that space is incredibly important. And it links again to social innovation, because innovating in that space will actually affect the sustainability of the livelihoods that people are able to derive from ASM. I wondered whether we could turn to this question of whether there are I mean, we make it sound like there's a sort of perfectible world there, but are there insurmountable challenges, or are there trade-offs? Are there things where if we improve these bits of mining, it's going to have these impacts? So I think of things like, a lot of people talk in this very rosy-hued way about the potential, you know, automatic mine. And I think, well, you know, in some places in the world that might happen and might be an achievable thing, but is it realistically going to happen in other places where maybe, you know, the cost standards trade-off will be different and that sort of thing? And will that then take away from potential, for example, for employment opportunities? So are there trade-offs that aren't so easy to work around in this innovation across the life cycle idea? Karen, do you want to kick off on that one?
Sure. So I'm just going to change from direct mining to actually mining of waste on this one. So one thing that I know there's talks in your sessions about looking at waste as a resource, and that's a theme that's been coming along for many years in terms of either remining to get the economic value out from maybe old tailings when things weren't as economic, or recycling or remediation. And all of those things are really important, both for the resource itself, but also to help public perception that things are being cleaned up. But that's not a perfect world either. And we see that in Cornwall, because in Cornwall we have the World Heritage Site of mining, the Cornish mining and mining in West Devon. And so there's heritage value for a lot of the mining landscapes that we see not only in the UK, but across the world. And by thinking about recycling or remediating some of these landscapes, we might be taking away from that heritage aspect. The other thing about that, of course, is also these mine sites are natural laboratories for us to study the effects of mining on landscapes, the effects of mining on humans. And because some of them have been around for a long, long time, things have adapted to them. So we see rare plants, metallophytes that are able to cope with high metals. We see rare lichens. And there's a whole other layer of interest around these new natural habitats. So the question is, do we remediate? Do we take it back to a pre-mining landscape? Do we destroy these new communities that have adapted? What do we do in this case? So while sort of cleaning up the landscape and solving all the environmental problems might be a good thing in some people's eyes, we might be then destroying what is actually adapted and then what is of interest to people from historical terms. So I don't think there's any right answer with that, but I think the best answer that we can see is communication amongst all the interested parties to come up with the best solution. So maybe perhaps not remediating the whole site, remediating part of the site that is really very detrimental or potentially detrimental to health, but leaving the scientific interest alone, still celebrating the historical importance of mining, so leaving the historical aspects. So it really, in my mind, comes back to the communication aspect from that regard. I think the innovation is there to do things. I think it's trying to get people accepting what we can do. Thanks.
Yeah, absolutely. But Jeremy, thoughts on these trade-offs, tensions?
Well, I think that if you look at some of the areas, such as along the mining value chain, for example, comminution, which comes to mind as an area of research interest to me, I think we're a long way from reaching the constraints, real physical constraints on energy efficiency, as from today's modern operations compared to what could be achieved. So to take that as a small instance, I don't think there is as we stand at the moment, an impasse where we can't accomplish energy reductions while also accommodating increased, demand. I don't think that's an impasse, and I think that it's a technological challenge, and and some of the presentations we've seen today have a direct bearing on that. If they, in due course, when they're successfully implemented on industrial scale. So I think that, of course, there is tensions always in terms of the economics, the growth. There's a clear tension in terms of some of the earlier presentations made about dropping head grades while having increased demand. That's clearly, there's clearly a interaction there, but there's a solution to that. And I think we've seen some of that demonstrated today in these really excellent student presentations.
Absolutely, indeed. And Catherine?
Yeah, I think the question of trade-offs is so important and so interesting, and I think there's real trade-offs sometimes between what's economically most suitable and what's environmentally most suitable. And I'll give you an example with the rare earth elements, which is something that I've worked on a lot. Now, the rare earth elements are absolutely essential for the high-strength magnets that are used to drive in the motors that drive some wind turbines and some electric vehicles. And it's expected that we're going to see increasing demand for the rare earth elements. But right now, that market is really pretty small. And there's a lot of complexity because the rare earth elements are a group of elements, and it's really only a couple of members of that group that you need for those magnets. So at the minute, most rare earth elements are produced in China. China really has a monopoly on that part of the supply chain. There's one major mine in Australia. And recently, China's been really trying to firm up on its kind of environmental conditions for producing the rare earths. But that has actually led to some production being moved to other countries. Myanmar is a big example. There's some production in India. And that production tends to be from deposits that are quite easy to access, but not the most environmentally friendly. Meanwhile, because China is covering the economics, if you like, it's not cheap enough for anyone to open any new rare earth mines. New rare earth mines aren't developing elsewhere. But the thing that we really know well is that production of bauxite, so production of aluminium from bauxite, actually produces waste that contains the rare earth elements. And there's been quite a lot of research done to show how you can get the rare earth elements out of that waste from bauxite production. Now, aluminium is one of our major elements produced all over the world in great volumes every year. If it were economically feasible to actually remove the rare earths from that waste and to produce them that way, then all of the world's required rare earth elements could be produced in this sustainable way just by extracting them basically as part of the processing of bauxite. But that isn't happening. So even although there's a potential for something really sustainable there, the economics mean that it's not going to happen. No aluminium company is going to pay to add this new process that is not going to make it very much money because the market for the rare earths is small. So there's a real trade-off issue there, and I'm sure that that's the same in many other commodities. That's just the example that I know about. And it's resolving that. It's understanding how to say the environmental cost or the environmental benefit actually is as important as economics. I don't know how we get around that at the moment.
That's a real challenge, I think. And I think that if you think about how some of these essential elements for sustainability are going to get mined and the challenge of the economics, it's sort of almost inbuilt however you go about trying to do it. The hurdle for doing that is so much higher than for some of the bulk metals. But you've led us fantastically, Catherine, into our, and Karen with your previous comments indeed, all of you, into what we're going into in the next session, where we're talking about mine waste, and there will be people talking about using mine waste for resources. So the innovation and the research in that space is incredibly important, but so also is the economics. And I think maybe the way in which the economics is framed is very much shaped by policy. So again, if you tune into the second showcase, we've got a session on policy issues there right at the end, which I think would position us really well to go back out from this conference and think about what we can do as a community that we've brought together, but also what we can go back out and what our ask is to other players who need to do their bit to help meet the world's resource needs. This is not something people are just doing for themselves. Anyway, thank you all very much. That's a really fantastic discussion. I think it sits really well between the talks we've already had and the ones that we're now going back into. I should have said at the beginning that biographies of our panelists are all available on our LinkedIn and Instagram pages, so please go and read more there about our fantastic panelists. But many thanks to you, Jeremy, Catherine and Karen. And now I'll hand back over to Michael.
Thanks, Nick.
Thank you, everyone. Michael, over to you.
Thank you so much, Nick. That was truly quite an informative panel. This is definitely what the conference is about, sharing ideas and breaking silos. I would really just love to say a big thank you to our panelists, and that is, let me just share the screen, and that is Mr. Jeremy, Dr. Karen, as well as Dr. Catherine. Thank you so much for joining us. We truly feel that your expertise in your different areas are truly invaluable. So, ladies and gentlemen, we are going to be moving on to our second video presentation session, and that is titled Sustainable Mine Waste. Sustainable Mine Waste Management, sorry. The title of the session is Sustainable Mine Waste Management, and we also have 3 video presentations from 3 students. And so we are going to go into the very first presentation, and that is from Isaac Haji from the University of Cape Town. So Isaac Haji from the University of Cape Town with the title, ARD Mitigation Using a Hybrid MICP Co-Disposal Method. ARD Mitigation Using a Hybrid MIPC Co-Disposal Method. Thank you so much, and ladies and gentlemen, please enjoy the video.
Good day.
So the video is gonna up just now. Sorry guys, this is what life is about, the little issues, but I hope you guys are still having fun.
My name is Isaac Haji. Good day. My name is Isaac Haji. I am a PhD student in the CIBA Research Group at the University of Cape Town. My presentation is titled ARD Mitigation Using a Hybrid MICP Co-Disposal Method.
The exploitation of coal and metallic mineral resources results in the production of large quantities of waste containing significant amounts of sulfide minerals. These sulfides become susceptible to chemical and biochemical oxidation, producing highly acidic metal-laden leachates referred to as acid rock drainage. ARD is initiated at neutral pHs when sulfidic minerals are exposed to oxygen and water. The reaction results in the release of ferrous iron and acid into solution. At pH values greater than 4, ferric iron is removed through precipitation. However, as this reaction continues, more acid is produced and water acidity increases, resulting in the mobilization of metals from mine wastes. At pH values less than 4, the increased solubility of ferric iron promotes ferric-driven pyrite oxidation at far greater rates than those associated with oxygen-driven oxidation. In addition, as the pH decreases below 4, iron-oxidizing bacteria, many of which have adapted to pH values of between 2 and 4, increase the rate of iron oxidation by factors greater than 10 to the power 6. Thus, once the system reaches pH values less than 4, a self-perpetuating cycle of ferric-driven pyrite oxidation and regeneration of ferric iron is initiated. This reaction continues until the pyrite source is exhausted. ARD can be sustained for hundreds of years and is the single biggest environmental problem facing the mining and mineral industry. It causes a range of environmental issues, especially with regards to the loss of underground water resources, since water scarcity is already a serious global issue. ARD mitigation can be broken down into 2 broad categories: remediation and prevention. Remediation works on treating ARD that has already been generated and includes the treatment of ARD with lime, anionic bioreactors, constructed wetlands, and permeable reactive barriers. As the name suggests, the aim of ARD prevention techniques are to prevent the generation of ARD. These methods include the use of water covers, bactericides, organic acids, flotation, and co-disposal. One of the methods that will be used in this study is co-disposal. This method involves co-disposing or blending reactive mine waste with potentially acid-consuming or alkaline-producing material. Studies have shown that the short-term prevention of acidic water discharge is largely dependent on the neutralizing capacity of the neutralizing material. However, once the buffering effect is depleted, the long-term inhibition of acidic water discharge is dependent on limiting air and solution flow through the co-disposed bed. Non-homogeneous packing of mineral particles in packed beds promotes channeling, which results in hydrogeological instability. This is further aggravated at high aqueous flow rates, where continued mineral surface exposure to aqueous oxidants increases the generation of acidic runoffs. This leads to a decrease in bed geochemical stability and the formation of preferential flow paths. A compact bed limits the flow of water and oxygen through the bed, thereby preventing the oxidation of pyrite in mine waste. Previous studies have found that a loss in structural stability occurs due to the migration of fine neutralizing particles within the co-disposed bed, which leads to the potential opening of voids between the mine waste particles. This allows the easy access of gaseous and aqueous oxidants to the acid-generating mine waste, which leads to ARD generation. They also found that the accumulation of fine neutralizing material towards the bottom did not contribute to the neutralization of the permeate, nor did it cause a restriction in flow. Typically, tailings with a good acid neutralizing capacity are used as the neutralizing material in co-disposal. Good results have been obtained by using a co-disposal mixture containing 40% of tailings. However, some studies suggest the use of a co-disposal mixture containing as much as 80% of acid neutralizing tailings. This brings up questions regarding the availability of high volumes of acid neutralizing tailings, as well as the feasibility of such methods of ARD prevention. In order to address the aforementioned concerns in an environmentally conscious manner, in this study, the co-disposal technique is further explored together with a naturally occurring phenomenon known as microbially induced calcite precipitation. Bacteria such as Porosarcina pasteurii have the unique ability to produce significant volumes of urease, an enzyme that catalyzes the hydrolysis of urea into ammonia and carbonate. The degradation of urea in the presence of calcium results in the creation of favorable conditions for calcite precipitation in the extracellular microenvironment. MICP has been successfully used in heritage structure repair and conservation, bioremediation, and biocementation. Seen here is a photograph of Chapultepec's castle in Mexico, where MICP was used to repair worn-out monuments. Onto the mechanism of MICP. Urea that enters the bacterial cell is broken down into ammonia and carbon dioxide. These are transported outside the cell, where the ammonia is hydrolyzed into ammonium and hydroxide ions, which increase the pH of the environment. The carbon dioxide reacts with hydroxide to form bicarbonate, which results in the formation of calcite in the presence of calcium ions. The calcite then attaches to the cell membrane to form a nucleation site for precipitation. MICP has the ability to cause short and long-range clogging in porous media, improve shear strength, and reduce water permeability in soils. As mentioned previously, MICP also leads to an increase in the pH of the microenvironment. Biosandstone has been produced using MICP, which resulted in a material with high shear strength, and scanning electron microscopy studies have been conducted to demonstrate the ability of MICP to bind sand particles. These studies suggest that MICP has the potential to reduce voids and improve bed stability in co-disposed tailing beds. The increase in the pH of the microenvironment is significant in this study due to its implications with regards to ARD. Firstly, the increased pH provides a suitable microenvironment for the survival and growth of Sporosarcina pasteurii. Secondly, it could relieve the neutralizing burden of the acid neutralizing tailings and may result in less material being required to achieve satisfactory ARD mitigation. And lastly, this study will test whether the increase in pH due to MICP can provide sufficient acid neutralizing capacity to soil, thereby eliminating the need for acid neutralizing tailings, which may not be easily available. Physically, Calcite produced via MICP will be used to mitigate the exposure of the mine waste to natural elements by creating a reactive barrier to oxidants that promote the onset of ARD generation in waste heaps. Due to the physical effects of MICP, the calcite precipitate will bifunctionally provide structural stability, supporting the reduction of seepage often associated with oxidative weathering, thereby preventing the emergence of a self-perpetuating ARD generating cycle. To conclude, this study ties in with the overarching theme of sustainable development in a few ways. The decrease in the pH caused by the hybrid MICP co-disposal method will lead to a decrease in ARD seepage, which positively impacts the SDG goals related to clean water and sanitation, life below water, and life on land. Since the hybrid MICP co-disposal method is a tool for ARD prevention, it can be incorporated into the development, operation, and closure phases of mines, which positively impacts the SDG goals related to sustainable cities and communities, as well as responsible consumption and production. These are my references, and I'd like to thank you for your time.
It is really so refreshing to see the out-of-the-box thinking that comes when dealing with ARD generation. And honestly, this was a very well presented and very well explained project. So thank you so much, Isaac. I am now going to move on to our next presentation. And that is also from the University of UCT, or sorry, the University of Cape Town here at UCT. And the name of the presenter is Sage Govender. And the title of her presentation is Repurposing Mine Waste, a Mineral Sands Case Study. Repurposing Mine Waste, a Mineral Sands Case Study, and that is Sage Govender.
Hi everyone, my name is Sage Govender, and I'm a master's student with the Minerals to Metals Initiative at the University of Cape Town. Today you'll be hearing more about my research topic, which is titled Repurposing Mine Waste, a Mineral Sands Case Study. I hope you enjoy.
It is globally known that the mining industry produces the largest waste stream, where the commodity produced is far outweighed by the waste it generates. This is, however, continuously increasing due to mineral demand and advances in mining technology. But this comes with its own suite of problems. The conventional disposal and storage of solid mine waste takes permanent residence on land, which requires costly long-term management and poses risks to the surrounding environment and communities. Prime examples include tailing dam failures, seepage from these facilities into water sources, and suspended dusts that can extend into perpetuity, thereby contributing to the unsustainability characteristic of the linear economy in mining. Additionally, this represents the loss of potentially useful or valuable material that can be reprocessed or repurposed on a case-by-case basis for socio-economic benefit. Mine waste valorization therefore also contributes towards the goal of the Global Tailings Management Standard by reducing the waste burden and lowering chances of long-term pollution. Globally, many applications have been explored for the various types of mine waste, which range from construction and industrial materials to landscaping. This displays the concept of a circular economy based on principles of industrial ecology, which just promotes the use of waste as a secondary resource and carries the potential to create downstream industries. These outputs of mine waste usage therefore have the potential to attain many of the Sustainable Development Goals. South Africa likewise faces this global waste problem and has explored some of the options for repurposing solid mine waste. Focus has been placed on our major coal and gold sectors. However, no or limited studies on the application of such approaches have been considered for our mineral sands sector. This small and often neglected sector ranks second in the world in terms of the production of titanium and zirconium for minerals like ilmenite, rutile, and zircon. The extraction of heavy minerals from mineral sands during open pit mining involves dredging or excavating the unconsolidated coastal sands. These deposits, however, only contain about 10% of total heavy minerals. This leaves at least 90% to be disposed of in waste storage facilities, which highlights the waste concern. The repurposing or reuse of mineral sands, therefore, becomes a very important issue to reduce this concern and the associated effects. Due to the lack of previous research addressing mineral sands waste valorization approaches, potential opportunities were investigated by reviewing existing approaches for solid mine waste. For the purposes of this project, tailing valorization opportunities were focused on. These included fine aggregates that can be used in construction materials such as wall mortars and renderings, methods of backfilling and co-disposal, which refills the mined out pits and is used to neutralize acidic wastes in some cases, brick making utilizing methods of clay firing, cementing, or newer methods of geopolymerization, ceramics for use as tiles, foundry sand for molding casts, and fabricated soils for use in mine rehabilitation and crop growth. In reviewing these approaches, 3 prominent points stood out. Firstly, all these approaches used waste with a silica-rich base component in the form of quartz. Secondly, the deleterious metal content is important to understand due to their effects on production chemistry. And thirdly, particle sizes will have an effect on the product strength, so it is important to determine the size fractions of the waste. These points, however, are purely based on laboratory studies and lack in an interdisciplinary approach. With this in mind, my research was designed to investigate potential opportunities for repurposing mineral sands mine waste, not only based on consideration of its physicochemical properties, but will also try to holistically consider the implementation of the approaches in context. This will be achieved in 3 phases. Phase 1 will investigate the physicochemical characteristics of the mineral sands mine waste. Phase 2 will apply a decision support framework to aid the identification of potential opportunities for repurposing mineral sands mine waste holistically and in context. And Phase 3 will demonstrate proof of concept for 1 or 2 of the most promising opportunities for repurposing mineral sands mine waste. In investigating the physicochemical properties in Phase 1, a variety of analytical techniques will be used. Particle size determination will be carried out using sieving and instruments for laser diffraction. The chemistry will be analyzed using inductively coupled plasma mass spectrometry and X-ray fluorescence. And lastly, the mineralogy will be determined using quantitative evaluation of minerals by scanning electron microscopy and X-ray diffraction with Rietveld refinement. Phase 2 considers technical, economic, environmental, and social aspects. This requires an in-depth, semi-quantitative study for each consideration. So, for example, the environmental considerations will include looking at each approach's ecological sustainability and processing, the quantity and hazard state of waste it generates, as well as quantifying the potential water and energy consumptions. These will be combined with the physicochemical properties in the application of an existing decision support framework, which will enable the selection of the most appropriate option or options from the waste valorization approaches reviewed in a local context. Phase 3 will demonstrate the proof of concept of the selected approach or approaches by experimentation once Phase 2 is completed. The product of this will fall under the 3rd technology readiness level, which concludes the research phase. Further development outside the scope of the study will proceed from level 4. The expected results from each phase will contribute the following. The physicochemical characterization in Phase 1 is crucial in determining the secondary usage of the waste. This will also contribute to the limited knowledge of variation within mineral sands mine waste. The application of a decision support framework in Phase 2 will introduce a holistic set of considerations involved in selecting approaches for mineral sands mine waste in context, which is also limited in waste valorization studies, but is slowly gaining traction. And lastly, Phase 3 will practically confirm theory. This sits at the lower end of the technology readiness levels, but will provide a base from which to further develop the approach or approaches. So, in a take-home message, this project will contribute to sustainable processing and closure, while addressing a number of the Sustainable Development Goals. Mine waste usage promotes responsible consumption. This strives to decrease the negative environmental impacts associated with mine waste storage, while simultaneously encouraging innovation and potential downstream industries. And ultimately, the knowledge procured in the study will add to the limited global research on mineral sands mine waste valorizations. Thank you.
Thank you so much, Sage. That was quite a lovely presentation. To think that something as simple as sand could actually be involved in such a complex framework in order to bring about a circular economy, this shows that we really should never take anything for granted. Now, our next and final presentation for this session is also sees us departing South African shores and going all the way back to the University of Queensland, Australia, in which Nicola Branch is going to be presenting on characterizing the impact of dust on the respiratory health of coal mine workers. Characterizing the impact of dust on the respiratory health of coal mine workers. Ladies and gentlemen, Nicola Branch.
Hello, I'm Nicola Branch, and today I will be talking about the characterization of particulates in underground coal mines in Australia, which is the focus of my PhD. This is part of a broader strategic gap analysis of particulates that David Cliff and myself are undertaking at the Minerals Industry Safety and Health Center, aka MISHC, within the Sustainable Minerals Institute at the University of Queensland. By characterization, I mean I'm looking at the chemical composition, particle size distribution, and shape of the particles present in the respirable fraction. The respirable fraction of dust are those particles less than 10 microns in diameter, which are of particular concern because they will penetrate into the alveoli in the lungs and cause scar tissue, which can lead to coal workers' pneumoconiosis, aka CWP or black lung, and a host of other mine dust lung diseases. I'll start with a bit of history about the resurgence of CWP in Australia. Next, I'll talk about the samples that were collected and the methodology for this research. From there, I'll discuss some of the preliminary data and its significance in controlling mine dust lung diseases. For 30 years, Queensland hadn't reported a case of CWP. That is, until a retired coal miner in his 70s was diagnosed in 2015. This was just the tip of the iceberg, as Queensland started to come to the realization that it hadn't been eliminated, it just wasn't being detected and reported. The Guardian called it a perfect storm of regulatory failure, indifference from the mining industry, poor dust control, and patchy health monitoring. This led to a parliamentary inquiry into the re-identification of CWP in Queensland, which recommended a number of changes to industry. Since then, the industry and regulator have made great strides in the control of dust underground, the monitoring of worker exposure, and the health surveillance scheme. But in many cases, the damage from coal dust exposure has already been done. As of 30 September 2020, there have been 187 mine dust lung disease cases diagnosed in Queensland since 1984. The figure on the right illustrates these mine dust lung diseases as reported to Resources Safety and Health Queensland. The teal color represents the cases of coal workers' pneumoconiosis, while the black represents cases of silicosis, and the light gray are cases of COPD. As you can see, the majority of cases are not CWP. In fact, only about a third are CWP, and a growing number are silicosis and COPD. COPD stands for chronic obstructive pulmonary disease, which is an umbrella term for chronic bronchitis and emphysema. There has been a fair amount of research done on the characterization of coal in the past, but this has always relied on taking a sample of coal from the coal seam and crushing it to analyze its components. And a number of these studies complain about how hard it is to crush the coal to the desirable size fraction. And this leads to an interesting paradox. If you're having trouble crushing the coal to that size fraction, is it actually present in the mine in that size fraction? More on that later. I have been using respirable cyclone elutriators to collect the dust in the respirable fraction that exists in the ambient air of the mine. It's not just the coal seam contributing to the respirable dust. It can also be the stone roof or floor, or stone bands within the seam, the stone dusting practices, the vehicle traffic, and possibly other activities going on in the intake airway, like shoveling. In this video, you can see the collection setup on a continuous miner in a Queensland underground coal mine. The spotlight shows the dust migrating from left to right across the face towards the cyclones. The blue blinking lights are the pumps that are drawing air through the cyclones. And the square metal frames were designed to hold the pumps and cyclones in the ambient airstream. In this case, it's just in front of where the coal workers bolting the roof would stand. These are the same respirable dust sampling units that are used for compliance monitoring to measure worker exposure. I use a different filter type in the cyclone to collect the dust that can be analyzed using scanning electron microscopy. Initially, I was sending samples to the States for analysis. Professor Emily Sarver and team at Virginia Tech had started analyzing samples from underground mines in Appalachia, as 1 in 5 underground coal miners with 25 years experience there had CWP. This graph shows a comparison of the chemical composition of the respirable dust in continuous miner sections in the US versus Australia. The light blue is the carbonaceous material, which includes the carbon particles, which is both the coal dust and diesel particulates. As you can see, in many cases, very little of the coal dust is actually coal. There's a large portion of aluminosilicates in orange and some silica represented in red. The carbonates in yellow are mostly stone dust. The dark blue is mixed carbonaceous material, and there are occasionally heavy metals or other particulates present. Except for Mine 3, who is cutting an area of stone in the working section, the Australian mines seem to have relatively more carbon in the samples than the US mines. This may be because Australian mines are typically leaving coal roof and coal floor. In the past year, I've been able to get these respirable airborne particulate samples analyzed in Australia. This can now be done at the UQ Julius Kruschnitt Mineral Research Center, abbreviated JKMRC, on the Mineral Liberation Analyzer, or MLA for short. The MLA is normally used to identify minerals in polished sections of drill core or lump material. And analyzing for particulates on filter is a new technique. Michelle Elms in the geology department has recently completed her PhD on the development of a methodology for particulates on filter using the MLA. With the MLA, I was able to identify 26 different mineral types as opposed to the 7 broader mineral categories in the US analysis. Historically, the characterization of dust in the 1980s was only able to look at the components of dust and the overall size distribution. With this technique, I can look at the individual particles for their size, shape, and chemical composition. This allows me to determine a size distribution for a particular mineral component. These samples were analyzed on the MLA. They were collected from 3 mines that are different mines and seams than the previous slide, so a direct comparison of the 2 methodologies cannot yet be made. The major trends hold the same, with relatively more carbon in the samples and just a small amount of quartz. While 26 different mineral components have been detected, I've removed the minor components for clarity of the slides, so you may notice that some don't add up to 100% now. This figure shows the particle size distribution for the carbon, aluminosilicates, and silica for mines 1, 2, and 3. These were calculated by measuring the largest dimension of each particle and assigning them to the appropriate bin, which is 0.1 microns in size. As you can see, the chemical compositions are very different. Mine 1 has a similar particle size distribution for carbon and aluminosilicates and very little silica. Mine 2 has a much larger number of smaller carbon particles than aluminosilicates, and again, very few silica particles. Mine 3 is very different in nature. For mine 3, the aluminosilicates dominate the sample, and there are also a large number of silica particles present, especially in the smaller size fraction. There's almost no coal in the sample, as illustrated by the blue carbon line on the bottom. MISC is currently working on a gap analysis of particulates in the mineral sector, which aims to identify the current gaps in our understanding of particulates and identify areas for future research. I'm still in the process of putting together the findings from the analysis conducted so far at the coal mines, and there are plans to start sampling the metal mines as well. That concludes my presentation, and I want to thank you very much for listening. I hope this gave you an idea about the challenges we face in preventing mine dust lung diseases and why it's important to be able to characterize the dust being generated in the mines with the goal of being able to understand the variety of particulates mine workers are being exposed to. This presentation also illustrates just how different the silica content and size distribution of the silica can be in different seams. Thank you.
Thank you so much, Nikki, for that presentation. What I found really sobering about it was definitely the human aspect. We shouldn't take for granted that the work that we do can have a profound impact on the lives of our fellow human beings. So thanks again, Nikki. Ladies and gentlemen, that brings us to the end of our second session. If you guys really enjoyed it, then I would like to encourage you to please make use of the Q&A function, because we're about to head into our second Q&A session. And I am gonna call back Catherine, who's gonna take us through it. So Kath, the floor is yours.
Hello again. So I've got a couple of questions here for Ishak, if you don't mind. The first being, can MICP be used to increase the percentage of solids and stability of tailings?
Hi, everyone. Thanks for having me. Yes, there's actually, to answer the question, yes, there has been a few studies on dust suppression, which ties in quite nicely with the last presentation, where they tried to use MICP to prevent dust formation in tailings heaps. And they found quite good results, actually. The upper 3 centimeters of the dust heaps formed a nice crusty barrier, which suppressed dust throughout the environment. I hope that answers the question.
Thanks so much, Ishak. Okay, I'm going to go over to Sage now. And the question is, mineral sands waste is normally benign silica sand that's usually returned to its source to minimize local impact, such as being returned to the beach. When not returning this waste to its source location in mineral sands mining and using this benign sand for other purposes, how do you propose to minimize the impact on the local environment?
Hi, thank you for the question. Yeah, so basically in South Africa, especially, it's required for mining operations to return their waste, to backfill their waste into the mined out pits. So by using, so one of the options, if not backfilling, is going to be some of the approaches that I have outlined. and taking into consideration, the economic, environmental and social aspects, as well as the technical aspects of using those approaches. So hopefully by using the waste that would otherwise be long-standing, it would reduce some of the environmental impacts. So as I said, if it's long-standing, then you have dust that can fly into the surrounding atmosphere. You have potential seepage into water sources. And then a special South African problem is that immigrants and low-income communities do tend to move into these lands that are unoccupied, and so that can be very potentially dangerous for their health as well. So it's something to take into consideration.
Thank you so much, Sage. That actually leads me into the next question that we have from Nikki, and that's just a question on: are you planning to potentially investigate the particulate dust compositions and size fractions in non-coal mines?
Yes. Actually, my next steps will be to start looking at some of the metal mines, which I think will be very interesting given the technique I've got with the MLA to be able to detect all those different chemical compositions.
Okay, amazing. I have one more question for you, Nikki, actually, and it's last quick question. And can the shape of the particles change the risk of the respiratory diseases? Can that be linked to any geological aspects?
Yes, so there's what we call elongate mineral particles, which are particles with a length to width ratio of greater than 3:1. And what those particles can do is if they go in the short way into the lungs, they can penetrate deeper and then turn in the lungs. So they will cause more scar tissue. But the way the sampling is done is based on aerodynamic equivalent diameter and not just the particle diameter. So because with the one thin dimension, they act like a much thinner particle, you do have greater risks from those particles.
Thanks, Nikki. Jeepers. I think I've got a much more deeper appreciation for my respiratory system, especially now given the pandemic. So yes. Thank you for that. I'm going to hand back over to Michael. Thank you so much, everyone, for your questions. Again, if you have any more questions for the speakers, please feel free to contact them via email or on LinkedIn or other social media platforms. Thanks, everyone.
Thanks so much, Catherine. I also definitely appreciate my respiratory system as well. So that brings us to the end of our second Q&A session, but we are moving straight along into another exciting video session. And this is our third session of today's showcase. And the name of the session is basically, it sort of leads on from the previous one, and it is about sustainable mine closure. Sustainable mine closure. And our very first presentation for this session is from the University of Queensland, and it goes, the presenter's name is Joe Hamago with the title, The Social Complexities of Mine Closure in Papua New Guinea. The Social Complexities of Mine Closure in Papua New Guinea. Ladies and gentlemen, please enjoy Joe Hamago's presentation.
Hello everyone, my name is Joel, and I'm currently a full-time PhD candidate at the Center for Social Responsibility in Mining at the University of Queensland. My research investigates the social complexities of mine closures, and I'm conducting a case study in one of the unoperational mines in Papua New Guinea. The Tolokuma Gold Mine is a small underground mining operation that began in the mid-1990s and passed through a series of different owners before its liquidation in 2019. The mine site is very remote in a mountainous region of the country, and access to site is only by air or through bush tracks. by virtue of its location and the challenges of access has made it a difficult place to do business. In Papua New Guinea, the concept of land ownership characterizes the social process of exclusion, participation, and the overall politics of agreements in natural resources development. This is because over 90% of land is held under customary tenure, and this is enforced by the country's constitution and various acts of parliament, leveraging the landowners in a position of power to negotiate or otherwise in agreements relating to land, access, compensation, and other benefits. For indigenous communities, mine operation at its various stages has a complex and nuanced connection to their livelihoods and the means of social production. When mine becomes unoperational, under whatever circumstances, this can trigger other effects on their social environs. Mines become unoperational under different conditions. As a requirement by state regulators, mining companies prepare a mine closure plan at the conceptual development of the mine and progressively update and submit these closure plans to the state throughout the life of the mine. Considerations towards the social aspects are typically a couple of pages, as opposed to technical and environmental aspects in closure planning. This is because the social aspects are difficult to predict, and in many ways complicated by their inherent connection to political, cultural, and institutional dynamics that exist within the society. In a country where the regulatory policies and regimes on contemporary mine closure standards that are not fully developed, companies are most likely to default on their closure obligations. My research is focused on understanding the art of negotiating the governmental and corporate goals into the social dynamics and how this can be framed in mine closure discussion. The overarching question is, how does this complex socio-economic, cultural, and environmental aspects from an indigenous perspective is merged into mine closure? Here, I am interested in the governance and regulatory aspects that guide mine closures and the gaps, which as a result of the complexities of the local social organizations cannot be adequately captured within the regimes. So this research hopes to untangle some of the social complexities and massage them into the governance framework so that the closure goals can be clearly defined and articulated.
If the adjectives short and sweet were in the form of a mine closure presentation, that will definitely be Joel's presentation. Concise, to the point, and impactful. Thank you, Joel, for demonstrating the efficient and sustainable use of our time. Our next presentation sees us back in South African shores with a presentation from Tapiwa Chimganda at the University of Cape Town, with the title, An Integrated Approach for the Transformation of Post-Mining Land Use in South Africa. An integrated approach for the transformation of post-mining land use in South Africa. Ladies and gentlemen, Tapiwa Chimganda.
Good day. My name is Tapiwa Chimganda from the University of Cape Town with the Minerals to Metals Initiative, and today I will be presenting on an integrated approach for the transformation of post-mining land use in South Africa. Mining is a temporary land use, and as more and more operations come to the end of their mine life or close due to geotechnical or environmental issues, the mining industry is increasingly grappling with the question of what happens beyond mining and what do post-mining futures look like for different regional contexts. Worldwide, most post-mining land use practices are not sufficiently developed to transition land into sustainable post-mining landscapes and build resilient economies. From the S&P Mine Project database, out of 1,800 mines documented as closed, only 141, which is around less than 10%, are actually defined as having been repurposed or transitions. There are very limited examples globally of what is deemed as successful post-mining transitions. Common global examples of mines that have been repurposed or transitioned into clearly defined post-mining land uses include the Eden project in the UK, which was a clay pit mine which was repurposed into the largest indoor forest housed in biomes. Another example is the Kubon Raya Megawati gold mining area in Indonesia, which has been transitioned into a botanical garden. However, for the South African context, there is the complexity around communities living in close proximity to mines. Communities depend on mining companies not only for jobs, but for services and infrastructure. Therefore, the narrative and approach around post-mining land use needs to be rather about transformation, transforming the landscape to build resilient communities. Adding to the complexity around mining communities in South Africa is the clear downscaling of the South African mining industry. Therefore, post-mining land use and approaches are a pertinent dialogue for the mining industry. There's been a clear downscaling over the last 10 years, especially led by the closure of gold mining operations, where several mines are coming to the end of their life, leading to around 90,000 job losses. However, there are very few operations that have clearly moved into post-mining phases. Post-mining transformation will, however, depend on what is the mine type, the environment, policy, community proximity, and the dynamics with the community and the mining area. But how do we make these decisions around what the future looks like? What are appropriate post-mining land use? How do we mitigate the various impacts, the environmental impacts, the socioeconomic impacts, such as job losses? And how does this tie into regional development? And where do we then begin to say we are building resilient communities and really answering the question around mining being a catalyst for sustainable development? The objective of this research project is therefore to investigate the potential to integrate mine closure planning, socioeconomic developmental planning, regional post-mining land use planning for an integrated approach to post-mining land use transformation for South Africa. To investigate the potential for an integrated approach for post-mining land use in South Africa, the research first looks at building a conceptual framework through initially understanding the key issues in South Africa through a desktop study by looking at what does post-mining transformation actually look like or mean within the complexity of a South African context, and why an integrated approach is actually needed and what key elements would be needed for an integrated approach. The next would be to evaluate the key themes in the South African post-mining space, looking at interrogating the discourse, identifying and categorizing those themes which emerge within the South African post-mining space, and looking at how can a multidisciplinary approach be used to understand the different factors that influence the discourse, the decision-making within post-mining transformation in South Africa. Then, by conceptualizing a framework for an integrated approach, one can start to map a conceptual approach and contextualize the factors and also evaluate how this can be applied to now unpack the potential to integrate or formulate an integrated approach for post-mining land use in South Africa. Looking at some of the themes that start to emerge out of the literature and rhetoric within the South African post-mining arena, some of the key aspects that start to present themselves include mine closure planning, decision-making, social impact, governance, leading into who are the stakeholders, responsibilities, the conflict around those responsibilities, the power dynamics, and the roles. By looking at these themes, one can start to understand all the factors at play within the post-mining arena. The next step would then to be to understand how to categorize the different aspects. The categories that start to emerge under which some of the themes that have been identified fall under are the problem, the politics, policy, and practices. Some of the themes which have been identified within the post-mining arena in South Africa can then be categorized, and one can start to conceptualize the approach and understand how these themes interact. Looking at work developed by Kingdon in 1995, who looked at how problems, policy, and politics interact in a multiple strains framework to inform agenda settings around social conditions, and Fowler in 2018, who then expanded this framework to look at implementation and interactions of social and environmental conditions. What is stipulated is that these streams interact in an interaction window, which then informs practices and implementation. Why this is important is that you can then link back to how this informs the key themes, the categories, and understand a conceptual approach for an integrated approach to post-mining transformation. Everything together, the themes, the categories, and borrowing from Kingdon and Fowler, who looked at social conditions and environmental conditions and the interactions of the different streams, one can then start to conceptualize a conceptual framework for post-mining transformation within South Africa. Looking at the problems and what are exactly the problems within South Africa, such as an insufficient transition to post-mining land use, stakeholder consultation process, the conflict around that, and the different policies which bound or frame the arena, and looking at the politics, the agendas, the advocacy groups, the labor conflicts, and looking at how those streams interact to then inform practices around post-mining implementation. And we can then now to understand how this informs current approaches and how emerging approaches can be unpacked and understood and evaluated. What this work highlights is how engaging transdisciplinary methods can enable the redefinition of complex problems and approaches, and how mapping the interactions of the different themes under the categories, the problems, the policy, the politics, can inform how current practices are approached, and also one can begin to understand how emerging practices can be developed and approached. A network of the relevant stakeholders can also be built by looking at the different role players who are involved within the different streams. And through understanding this, one can now understand the power dynamics at play within the post-mining space within South Africa. Through applying this multiple streams framework, an integrated approach for post-mining can now be conceptualized and evaluated. And the next step would be to understand how to then analyze the potential for an integrated approach to post-mining land use in South Africa. Thank you.
Thank you very much, Tapiwa, for that presentation. This just goes to show the importance of localization. Just because something works in a particular instance does not mean that it can be blindly applied everywhere. As someone once said, take the text out of the context and you are left with a con. So thanks, Tapiwa. That was our final presentation for today's showcase in terms of video presentation. Sorry, no, this one coming up is our final one. And it is from Andrea Aratia Sola, a student from the University of Queensland, with the title, The Design of a Framework to Optimize the Process of Post-Mine Land Use Planning. Design of a framework to optimize the process of post-mine land use planning. Ladies and gentlemen, please join me in enjoying Andrea Aratia Sola's video.
Hello, my name is Andrea Aratia Solar. I'm a PhD student at the Center for Social Responsibility in Mining in the Sustainable Mineral Institute at the University of Queensland, Australia. My research is focused on post-mine land use planning. Specifically, I seek to design a framework intended to facilitate the post-mine land use planning process. In this slide, you can see what I will cover in this presentation. I will start with a global context related to my research. I will briefly talk about multi-criteria decision-making. Then I will discuss previous studies that are related to my research. I will present my research question, aim, and objectives, followed by the proposed decision-making framework and the methodology that's behind it. Climate change concern and public pressure have triggered a global energy transition that seeks to decarbonize the global energy matrix. This energy transition means that the coal demand will decrease in the medium to short term. As in any other market, when there is no demand for a product or the product gets unprofitable, the expected trend is to stop producing that product. In this case, the product affected will be thermal coal, implying that a large number of coal mines will close before planned. Mine closure brings the dilemma to plan for what is after mining. The decision process to determine post-mine land uses deals with critical decisions across different scales and has complex issues to consider. Current research methods that deals with post-mine land uses are generally time-intensive and essentially case-based. Currently, there is a need for a framework that can incorporate multidisciplinary data for different stakeholders to consider, and that can be used at the regional scales. This research focuses on these aspects by designing a multi-criteria decision-making approach to deal with the post-mine land use planning. A brief introduction to multi-criteria decision-making. It is a branch of operational research and was developed in the 60s. Multi-criteria decision-making explicitly evaluates conflicting criteria in a decision-making process. It uses different mathematical approaches or methods. The method used or applied depends on the context that the multi-criteria decision-making process is being used. Bandyopadhyay and Chattopadhyay first applied multi-criteria decision-making to post-mine land use planning for a study that was commissioned by the Alaska federal government in 1984. Between them and the next study applying multi-criteria decision-making within the post-mine land use planning context, there is more than 20 years gap. From this table, we can see that multi-criteria decision-making applied to post-mine land use came back in 2009 with a work called Sultan Mohammadi. Also, from this table, we can see that a few methods are commonly shared between different papers, like AHP, PROMETEE, and TOPSIS. All of the papers that are in this table use decision makers' participation. However, not all of them mention the background of those decision makers. For the paper that do mention the background, is usually a mining background. Here we have the research question of my research. And it's how to optimize post-mine land use planning while reaching consensus among stakeholders. The aim is to design a framework to optimize the process of post-mine land use planning by integrating the unique environmental and technical characteristics of mining affected areas together with stakeholder values. I have two objectives that are related to the aim of the research. Objective 1 is select a land use classification system and define post-mine land use attributes to recognize feasible post-mine land use alternatives while having a high consensus among local stakeholders. And the second objective is to design a multi-criteria decision-making process using an expert panel integrating local and technical knowledge. Let me introduce you to the decision-making framework that I have developed. It has 5 different stages, as you can see. The first stage is the process to identify land use classification and post-mine land use attributes. Stage 2 of the framework is a multidimensional spatial analysis specific to the study area. It will work as a filter. As you can see on the slide, it will be based on literature review and policy review. I will perform a spatial analysis, and luckily I will have interviews or workshops with key stakeholders. Stage 3 of the framework is where the data collection through an expert panel will happen, and the output of this stage will help to design the multi-criteria decision-making matrix that will be used in stage 4. Stage 4 of the framework is where the multi-criteria decision-making model runs. The output of this stage is a set of post-mine land use alternatives. Stage 5 of the framework is where a set of ideal post-mine land use alternatives are chosen from the output of stage 4. Now I'm going to explain the methodology that is behind the framework. Stage 1 will use the Australian land use and management classification. Post-mine land use attributes will be selected considering previous literature. As well, the attributes will be grouped in environmental, social, and economical and technical criteria. This is an example of the complexity of the post-mine land use attribute selection. There is a lot of data to consider, there's a lot of attributes to consider, but it's important to narrow them down just to make the model feasible. Stage 2 will pre-select the post-mine land use alternative. For that, I will use literature review and I will conduct a special analysis of the study area. Ideally, in this stage, a survey should be conducted to choose a set of post-mine land uses that will be considered for the decision-making process. Ideally, the participant on the survey should have a diverse background. For example, could be employees of the mine, local stakeholders, government employees, specialists in the mine closure, minorities, Aboriginals if the case, just to ensure that we have a diverse decision-making process and inclusive as well. Stage 3 of the framework is where the data collection through the expert panel is conducted through questionnaires. The multi-criteria decision-making matrix is designed in this stage as well. It will be based on the result of the questionnaires and will be the input for stage 4. I decided to use TOPSIS because this method can handle large number of criteria and options. It's a ranking method as well, that is what we are after. It can handle quantitative and qualitative indicators, among other reasons. Stage 4 of the framework is where the multi-criteria decision-making model runs. In this case, I will use AHP and Topsys method under fuzzy environment. This is the last stage of the framework. Here is where the final implementation of the post-mine land use takes place. Stage 5 defines a set of ideal post-mine land use alternatives. This set is a subset of the ranking of post-mine land use alternatives that is the output of stage 4.
Thank you so much, Aratia, for that wonderful presentation. It again just makes me appreciate the complexity of the decision-making process when it comes to post-mine land use. So again, what a wonderful presentation. And that brings us to the end of our third session about mine closure. I would like to just remind the audience that you are going to be able to vote for your Viewer's Choice Award. So you have now seen all of the videos for today's showcase, and you are in the position to sort of try and select which one you think actually deserves the award. So please keep that in mind when the option does become available. But though we are done with the video presentations, we are actually moving on to something that is quite exciting as well, and that is our very second panel discussion. And to introduce that, we are first going to have our Q&A session, who is going to be run by Catherine, and she's then going to segue into the panel discussion because she's also the moderator for that. So I am now going to pass over the floor to Catherine. So Catherine, please take the floor.
Thanks, Michael. Okay, so I've got a couple of questions for Joel. And the first question is, do you think that these particular social complexities that you observe or anticipate will vary within different mining communities? And if you do think so, in what way?
Hello. This is a very thought-provoking question. It will vary in many different ways, because in the absence of a legislative guidance on how benefits that should be accrued to the future by the mining companies, in the absence of such guidance, companies and communities and host local governments made ad hoc arrangements. So this complexity is tied around companies and communities also vary. So I cannot say for one size fits all, but it will vary significantly from place to place. Yes.
Yeah, it highlights the complexity of what we're sort of looking at. Following on from that, in terms of what social aspects do you, surrounding mine closure, do you think would be unique to Papua New Guinea? And do you think any of those could be useful in application to contexts such as South Africa or Australia?
I think it's one thing is about that really comes clear in my work so far is about agreements making and how agreements are made in the beginning with a clear picture of how the end would become. So if we make clear agreements with the community, then I think that the model of agreement making could apply to other jurisdictions as well.
Thanks so much, Joel. That's great. Thank you. Okay, so Tapiwa, I have a question for you. And the question is your research solely focused on South Africa, or do you envisage that your work would have implications for application elsewhere and potentially at similar mine types?
Yes, I think definitely the work is currently focused on South Africa because of the unique sort of space that a lot of operations in South Africa, actually there has been no large scale operation in South Africa that has transitioned into a clear post-mining phase. So yes, South Africa is the current case study that my work is focusing on, but I definitely think in terms of the approach that emerges, it could definitely be transferred or applied to similar contexts in other regionals. But I think from what Joel is saying, a lot of the aspects around the complexity within post-mining land use selection, a lot of them is contextual, but definitely there are certain, I think, fundamentals that could be transferred, especially in looking at all these frameworks around how do we actually integrate the environmental, the technical, and most importantly, the social economic aspects, which are often neglected.
No, exactly. Thanks, Tahira, that was great. I have one question for Andrea, and that is, do you think your methodology is applicable at various scales of mining, or do you think it's better suited to one or either traditional large or artisanal small scale mining?
Hello, thanks for having me here. I think it will be applicable for all sizes, but I haven't seen that specifically. My focus is in coal mining right now, and just because for the energy transition, but it could be applied to any size, including a small mining.
Yeah, I suppose you would just have to build that into your framework and your decision-making matrix to sort of account for those extra sort of nuances between the small and the large scale mining.
Because you have the spatial analysis, the stage 2, where you do the filters and you make the framework work in the situation that you want to apply it.
Yeah.
So in that case, it will be applicable to a small mining.
Yeah,
as long as
exactly.
Yeah.
So. Yeah. Thanks so much, Andrea. That was great. So we're going to close off the Q&A for this session. And again, if you have more questions for our presenters, please contact them on social media or email them. Their information is available on the conference proceedings ebook that we've made available on LinkedIn. And we're now going to go into our panel discussion for today. So I'm going to turn my video on because I'm moderating that. Hello. So this panel discussion is on the future of mining, and we're very lucky in that we have Matt Pyle, who's the Director of Technical Solutions at Ausenco. We've got Sue Harrison, who's the Deputy Vice Chancellor for the University of Cape Town, as well as the Director for the Centre for Bioprocess Engineering Research. And we also have Murray Hitzman, who's the Director of the Irish Centre for Research in Applied Geosciences. So before we kick off the discussion, I'm going to hand over to Matt to give us a presentation on Ausenco, because they are one of our fabulous sponsors.
All right. Good evening, morning, afternoon, wherever in the world you are. It seems we're doing a lot of these meetings these days. Can you all see a bit of a Ausenco splash back there? I can see a thumbs up. That sounds good. All right. Yeah, my name's Matt Pyle. I graduated from UQ in 2009 and have the pleasure of working with a number of bright, smart people that have come through programs like this. A lot smarter than myself, I'll be honest. And look, what I wanted to do now is just present a bit of a video that talks a little bit about Ausenco in, let's say, 3 or 4 minutes. Look, we're a mining services company. We're about 2,000 people strong. We basically do everything to do with minerals processing. So in the background here, you'll see a summary of what really makes us different. We sort of called this our purpose video. And so I'll just talk to some of the points that it raises here. But we were founded in 1991 in Brisbane, not too far from the University of Queensland. And we're always committed to getting the right people together to sort of get better solutions than our competition, other companies. So this statement here, a better way, is really what we're all about. We've lived through a number of commodity boom bust cycles, and that forces us to do things a little bit different and remain innovative. And these projects that you can see coming up on the screen at the moment are a number of world firsts. There's a lot of projects we've done, but here's some unique ones that sort of showcase unique elements in each and every case. So here we're sort of seeing projects through Southeast Asia, which initially were how Ausenco sort of cut its teeth. We challenged the way that plants were designed. We produced low-cost gold plants. And the designs, it's not uncommon that our designs save half the concrete and up to 80% of the steel, just by challenging things and doing things differently. We grew through a number of acquisitions in the mid-2000s. One of the acquisitions was PSI, which has designed 80% of the world's long-distance slurry pipelines. We've got infrastructure design services. We do a lot to do with ports and terminals. We have a part of the company called Ausenco Ryerson that does asset optimization. So they look at optimizing process plants and the equipment within process plants. At the moment, we're showing a project, Constancia, in Peru, which was our first really large project in Peru, and we added $800 million to the value of that project. When we took it over, that project wasn't viable, and now it's you know, a top producer for a company called Hudbay. At the moment, we're showing the Minas Rio pipeline, which is the world's longest distance slurry pipeline, and we actually operate that as well as designing it. We're running a mine up in North Queensland called Capricorn Copper, and we've increased its throughput by 50%. The slide's a bit outdated. It only said 30% when we put the slide deck together. We've got an environmental services company called Hemera, which is based in Burnaby, Vancouver, and it's about 250 people strong. And through Hemera, we do a lot of environmental consulting that ties in well with this ESG theme that we've seen through the conference this evening. So really, finding a better way encompasses most of what we do. We're strongly focused in community work, engage with our communities really strongly. One example of that is a company we work with called Regional Economic Solutions, which engages with First Nations. So fundamentally, I suppose, we're focused on people, empowering people and working together in teams. We work hard to break silos to add value to the world's largest and smallest projects. You know, and we're innovating always to sort of keep up with the times. Providing engineering services from, you know, all around the world is difficult at the best of times, let alone when you're in the middle of a COVID pandemic. But that hasn't stopped us, I suppose. We've still got about $2 billion worth of construction underway. A lot of that's at a major site we're doing in South America at the moment, and that site's COVID free. So we've learned how to manage COVID, for example, to sort of keep functioning during these times. So look, that's a brief background to Ausenco. In terms of today's panel's discussion, I'm really looking forward to getting into the topic and talking about how we can break the silos. Thanks very much.
Thanks, Matt. That was great. So I think, you know, just taking a little of your company sort of manifesto, finding a better way, I think that links quite strongly to what we're trying to do with this conference, and looking at the, you know, how we can mine for the future mining trends, innovation within mining. So I have a question that I'd like to pose to all of you, and I'll in turn go to each of you and you can give me your thoughts. What do you think are the trends in mining and its sustainability? Murray, would you like to go first?
Let me unmute myself so I can get there. Hello, thank you for inviting me. Trends in mining, there's several and some of them are conflicting. So as some of the presentation showed earlier, one of the big trends in mining over the last several decades has been increasingly mining lower grades of ore. And that has been a trend throughout the 20th and into the 21st centuries. I'm not convinced that that trend will continue as we move on in the 21st century. Because as it shows, we're increasing the amount of waste we produce as well as we mine the lower grades. And as many of the talks talked about, waste is a real issue with mining going forward. So perhaps, this is just sort of a radical suggestion, the mining companies really need to rethink about mining altogether and how they're approaching it. And rather than getting better ways to mine lower grades, we probably need to find better ways to discover higher grade deposits. So put it back on the exploration side, that we need to redo our jobs better on explorationists to give the mining companies better deposits to mine. Thanks.
Thanks, Murray. That was great. Sue, would you like to chip in there?
Thanks, Catherine. So in addition to mining lower grades, and the debate of whether we should or shouldn't, is the idea of mining more complex minerals, but also of being sure that we fully exploit the resources that we mine. So for a long time, we've been inclined to take what is easy to take quickly and to the level that it is, that it makes us a lot of money. Whereas actually what we need to think about is when we go into a resource, we need to take everything that is valuable from it. And actually we need to reuse what's not so-called valuable as well. So it's a different way of thinking about it. And it may not be the most, it may not drive on the highest profit in the initial space, which is highly unpopular to say, but the liability of leaving things behind and stockpiling them and having to deal with them later on actually ends up costing us far more. So thinking about how do we, when we go into a resource, how do we use it fully to its best advantage, maximize resource efficiency, and leave as little waste as possible, as benign as possible, with risk prevented. That's where we should be going.
Yeah, exactly. Thanks, Sue. Nat, from an industrial perspective, what do you think, or where do you see the trends of mining with respect to sustainability going?
Yeah, it's a good question, and it's hard to give one answer to it, I suppose.
Yeah.
When I look at where the industry has come from and where it's going, you know, you can trace a lot of decisions down to economics. And there was a good presentation earlier on that was talking about how that, let's say, value equation should include all aspects of ESG, and I wholeheartedly agree that it should, including what Sue was just talking about, like the legacies, for example, that sort of mine sites leave behind. So putting that as sort of the background to answering this question, we've seen over the years when head grades have been historically high, there's been a lot of focus on maximizing recovery. For example, we really take all the ore and grind it and float it and recover as much as we possibly can. And metallurgists of 30 or 40 years ago were trained a lot in maximizing recovery. As we go into lower and lower grade deposits, and that was, you know, largely the right thing to do, by the way. As we go into lower and lower grade deposits, and we see trends like economies of scale, the value equation changes a bit, and it's more effective to accept lower recoveries at higher throughputs. In other words, for the effort you're spending, you're getting more overall metal, but at slightly lower recoveries per ton. And it's a whole other discussion to get into whether that's good practice or bad practice, and there's arguments both ways. But at the end of the day, we are seeing lower and lower head grades and more complex deposits, and I'm sure both will be mined. But technologically, there are some big step changes coming in terms of how we consider processing, because as you get to the lower and lower grade material, it no longer makes sense to mill at all, because milling uses a lot of energy, uses a lot of water, emits a lot of carbon dioxide. There's a lot of good cases to say we need to sort of progressively reject waste through the value chain. And there's a lot of technologies like sorting, particle sorting, bulk sorting, better grade control in the mine, even better resource, you know, starting at the resource, understanding the mapping of the resource in the ground before you even explore it or mine it, all the way through to coarser grinding, coarse particle flotation, better liberation, pre-concentration. And, you know, you put a lot of those things together, and it's not that hard to imagine a mine site with half the water consumption and less than half the energy and power. So that's where I think we're going.
Yeah, I read somewhere that the future of mining is lean, green, and digital. And I think it sort of encompasses this sort of working machine and man working far closer together in a different way. With that in mind, though, so in the previous panel discussion, when we were speaking about innovation within mining, I think both Karen and Catherine brought up the brought up elements or aspects of reprocessing of waste. And what are your thoughts on transitioning? How do we actually transition to best practice resource efficiency so we can reduce waste and make it into a new resource, as opposed to leaving these legacy problems for other people to deal with? Sue, I don't know if you want to go first on that one.
Catherine, you know, it's a subject I like talking about, don't you?
I do, yeah.
So I do think we've got great opportunities to think completely differently about mine waste, and not to think about it as something which needs to end up in a pile or even be reburied underground, but rather to think about what's in that waste and how we can use it. So the part of it is recovering the values, which I think we're all onto, and I think we all feel very comfortable about. But part of it is, what do we do with literally the mineral ash, the real waste part of it, or the problematic things like pyrite. And more and more, I'm an academic, so I'm allowed to work at the side which is, you know, more into the future. We're able to make those materials into things which have value. So, for instance, I don't think the presentation was up this morning, but I'm sure there is one. The idea of taking the waste ash and using that as the basis of a soil, so that you can revegetate afterwards. Things like that allow you then not to have as much of a waste dump at the end of the day. And there are also fractions in there which can be valuable to one, so iron-based products and so on that we can create from these wastes. So I'm very into thinking about the waste and thinking about how we can use each part of it, and only wanting to dump the material that we absolutely can't use, and then to dump it in a way, as I said earlier on, which doesn't present a risk moving forward. And it requires quite a different mindset, and I think it's that change management which we're going to find quite difficult, but I think it's doable.
Yeah, thanks, Sue. So, Mary, I'd like to turn that same question to you, and just sort of build on that and say, what barriers do you sort of see in these sort of, you know, transitioning to best practice?
Most of the barriers are economic. Clearly, and the way they'll probably be overcome is through regulation. So, for instance, in the United States, coal mines, strip mines, are not allowed to, they have to remediate completely, so no pit is left at the end. And I suspect that within some of the young people's lifetimes listening, open pit base metal mines will no longer be allowed either. And try to think about remediating Chuquicamata or Escondida. Right? So it would bankrupt the companies mining them now, right? They're not economic. So I think moving forward, we have to think about this much more holistically. So Susan's right. We have to think about the waste as something that has value, because otherwise I don't think it makes economic sense. And if we're going to create pits or underground openings, how do we repurpose them for other uses after the mine? Right? Big holes in the ground probably can be used for other purposes if they're planned right to begin with. Right now, most companies, I would venture to say almost no companies, actually really do post-mine planning the way it should be done for the future.
Yeah, no, I completely agree. Thank you, Mary. Matt, so over to you now for the same sort of question. You know, Mari's brought up the really real issue of the economic sort of challenge associated with trying to, you know, force this transition towards sustainability within these sorts of aspects. So what are your thoughts on that?
Yeah, it's, I guess what was previously uneconomic to process is now becoming economic to process. I mean, 20 to 30 years ago, when we started building these gold projects, gold price was around that $250 an ounce mark. Admittedly, the dollars were deflated compared to today's values, but that's still quite low when you consider we're at 1900 US, I think. So, look, I guess to answer your question, with improving technologies, we are seeing that projects are more able to operate at lower capital and operating costs, and with lower impact and footprint. Operating costs for sort of, you know, large concentrators is around $6 a ton, and it would have been orders of magnitude more than that a century ago. So what that means is that you can look to treat waste from historic operations, which is really a good thing. And you know, a lot of projects are looking at this. It's really not uncommon that we look at projects that have been mothballed or looking to be brought back to life with a different approach or a different tack. And there's a lot of junior companies in the market that are holding onto these resources because they know that these technologies are coming, and they're making substantial differences to the way you process ore. So it's an ongoing cycle, and it's good to see. Some of the examples are that the technology specifically for retreating waste are things like coarse particle flotation, where you can you know, pull values out of tailings. There's improved reagent regimes and better understanding of the metallurgy. And there's also new leaching technologies that are, you know, things like chloride leaching. And there's a large chloride leaching project that BHP are doing at the moment in South America that, you know, that should run with a pretty low operating cost. And, you know, so these things aren't just out, you know, they are happening.
Okay, cool. Thanks, Matt. Okay, so I have one last question, and this primarily sort of stems from being a student at an academic institution. Do you feel or think that we are giving students and you know, the generation, the next generation, do you feel that we're preparing them adequately to enter into the mining and minerals processing sector with the way that we're teaching and training people now to actually facilitate the transition to where we actually want to go with mining? Mary, I don't know if you want to start us off there.
I can try. So I'm at a university now which doesn't have mining engineering at all, having come from one that did. So I can say that probably the number of places that actually are training people in the right way has shrunk dramatically. I think there aren't that many institutions on the planet that are doing it. The ones that are doing it, including the ones, you know, we had presentations from a number of the students, I think are doing it quite well. I think they are seeing that integration among many different technologies and fields is necessary. The one that I guess I see I'm very heartened by is my training originally was as an anthropologist as well as a geologist. And it's taken sort of my whole lifetime for, I think, everybody to catch up. Clearly, the social sciences have to be something that are very important to training people in the mining sector going forward. They don't have to be maybe experts in it, but they certainly have to be aware of the concepts and the promise that area holds for what we do in mining.
Cool, thanks, Mary. Matt, what do you think of the youths that you are absorbing into your company? Do you think that they're prepared to sort of, you know, meet the challenges that the mining sector is facing?
No, I think everyone who goes through university and comes out and wants to work in the mining industry is a champion. I think that, you know, you're good on it. Good on you, everyone. You're all legends. I think the problem is we don't have enough. So the issue in my mind is the negative stigmatism. I don't know if you'd call it that, but you know, the perception. So when I graduated, from UQ, there were close to 300 mining and minerals processing engineers. And I looked recently, I think this year they're expecting 21 and next year is 15 to give a relative benchmark on where the numbers are at. So that's the thing that really concerns me the most. Obviously with smaller cohorts, you get less interaction, less learning. I think the universities are doing a great job. I really don't see any problems there, but it's, as a society, we need to, you know, mining's a good thing, right?
Yeah. Thanks, Matt. Okay, Sue, you can close us off here with your thoughts.
So I think it's really interesting how differently we train people for the industry across the different universities. So the university I'm from has always been viewed as being a strong minerals university, and yet we don't have a mining and minerals degree. We have a chemical engineering degree. And the advantages and disadvantages of doing it in the way that you stick to the I guess the bigger discipline rather than the more specialized one. I actually think that at the moment, the need to be able to paint the broad picture is becoming stronger and stronger. And so even just the engineering discipline isn't enough, and we need to be able to bring the awareness in of the environment, of the water, of the anthropology, of the people interactions, of the law, and so on. So I think that's the real challenge to us who are in academia at the moment, is how do we do that? How do we provide a degree that has the depth of technical knowledge which is needed, and there is a depth of technical knowledge needed, but yet the understanding of those other aspects simultaneously. And that's where we have to get clever, because if we don't do that, I think it's really difficult for the ability to interact across those sectors. Maybe the point I want to make in closing is that to bring the mining industry back into the space that it's really that it's viewed, it's perceived as that exciting space, I think we're going to need to be able to look at the much bigger life cycle that happens in communities where mining happens, from right at the beginning and how it gets planned, right through to what's happening when those mines are all closed and what it's done for the community. So the ability of the actual process of using that resource to be able to contribute good into the society in which that resource was placed. And that needs the people involved in it to really be able to have that broader appreciation. So as academics, we need to think about how do we at least sow that seed during the training years of a student. Thanks.
Yeah, definitely. Thanks, Sue. I'm going to close out this panel now, but I just want to say a very, very, very big thank you to Murray, to Matt, to Sue for giving up their time to come and chat to us and give their inputs and just engage with us. It's been such an awesome experience to meet you all virtually. So yeah, thanks everyone. I'm going to hand over to Michael now for some closing remarks. Thank you.
Thank you.
Thank you.
Thank you.
Thanks, everyone. Thank you, Catherine, for that wonderful panel discussion. It was, again, very enlightening, and it's so nice to see the different points of view. Now, I think our audience, if you would notice, there is a People's Choice Award that is on your screens. So it is basically voting for your preferred presentation of today. Please note that this is going to also happen tomorrow. So there are going to be 2 choice awards. So the first one is for today's live showcase. And in about 12 hours time after this one ends, there's going to be another showcase and there'll be another award for the viewer's choice. So just to take you through the different awards, I'm just going to share my screen right now. So for the different awards, we have the big awards, which is the winner for, I think, for the different days, for both days. You have the winner that's going to receive 1,000 Aussie dollars. Then you have the runner-up who's going to receive 750 Aussie dollars. And the third position is going to receive $500. Now, this is for the overall winner for both sessions. But for the 2 sessions, we have divided the People's Choice Award. So for day 1 and day 2, the prize pool is actually 500 Aussie dollars, which is quite significant, I would say. So yeah, this is quite a very, very difficult decision to make, but please make it wisely. I could run through the different presentations. So I think the poll is going to be up for the next 1.5 minutes. So in the very first session, you had Joshua Rosera, who gave us a wonderful presentation about looking at utilizing space resources, going all the way to infinity and beyond, as Buzz Lightyear would say. In the first session, the second presentation was by Flav Andre, who looked at basically upscaling. The second presentation was by Daniel Hastings, who looked at incorporating governmental, environmental, and social factors into financial models in order to, to enable a better decision-making algorithms for the mining industry. And the third presentation was by Flav Andre, looking at HVP systems and how to basically upscale it. And in the second session, which basically was looking at sustainable mine waste management, we had ESAC with ARD mitigation, a hybrid system. We also had our fifth presentation was by Sage Govender with Repurposing Mine Waste, the mineral sands case study. And then we had Nikki, who gave us the wonderful presentation about characterizing the impact of dust on the respiratory health of coal mine workers. And then for the final session, our very first video was by Joel Hamago, who spoke about the complexities of mine closure in Papua New Guinea. And then the next presentation was by Tapiwa Chimganda, who looked at an integrated approach for the transformation of post-mining land use in South Africa. And the third and final presentation of the day was the designing of a framework to optimize the process of post-mine land use planning. And this was by Andrea Aratia-Sola from the University of Queensland, Australia. So those were the 9 presentations, and they were all really awesome presentations. So please do kindly cast your vote. And once that is done, we would then be able to basically tell you who won. And I think that is a great way to sort of end up this thing. So it closes in 30 seconds. So please do cast your votes, ladies and gentlemen. I'm sure the different participants are already thinking of what they're going to do with their 500 Aussie dollars. Not much due to the pandemic, but still, it's still, you maybe not going on vacations, but maybe buying yourself something nice, or, you know, who knows? There's so many possibilities. So I actually was one of the winners last year, believe it or not. So it is quite thrilling to be on the other side of the fence and sort of looking at other presentations and being the one that holds the power. But yeah, so great. I think the results are coming up, and I think we are going to be able to see who actually got the top vote. I do see them right here. So based on the results, it seems we have, is it a winner? We do have a winner, not a tie. We have a winner. Yes, and the winner is actually from the University of Queensland, and that is Flavio Andre, like Flavio Andre, or Flav Andre. I'm sorry if my pronunciation was a bit wrong, but Flav Andre, do you want to just say like a very quick sort of share your thoughts, how you feel about this, just to say, you know, thank you. Flav, is Flav in the building?
Yes, sorry, I forgot to unmute myself.
Okay.
So first of all, I'd like to thank everyone that voted for me. It's a pleasure to be here in these uncertain times, but we're able to host this event. And I'm really happy that my project got most of the vote, and it's a very important project for the future and the sustainability of the mining industry. So thank you very much.
Thanks, Flav. And that, ladies and gentlemen, brings us to the end of our session. So I hope you guys really did enjoy this live showcase. And I will just end, before I end, I would just want to thank all of our presenters. You guys did wonderful work. The video presentations were such top quality. For all our panelists, thank you so much for joining us. For all of our sponsors, we really do appreciate the time and the efforts and the funding that you gave to this conference. It was truly really nice to see you coming on board. And to our organizing committee, thank you guys so much for working so hard behind the scenes. It really has made quite an impact, and I hope that the audience does recognize it. I would like to remind everyone that there is another showcase tomorrow with all new presentations and panel discussions. Please kindly check the schedule for the appropriate time. It's going to be approximately 12 hours from now. So if you are able to make it, that will be great. The more, the better. I would like to end this with just a statement or just an analogy. Basically, as comfortable as silos are, in many cases, rather than protecting us from the danger of what lays outside, they actually blind us to the ideas and opportunities within our reach. It is only through collaboration and the breaking down of silos that we as the human race can progress. So thank you so much, everyone. I hope this does inspire the breaking of silos. From me and from the rest of the organizing committee, we would like to say thank you and God bless.